should be live.
Okay, I'm Tim Ventura, and welcome to another edition of APEC, the APEC conference. This is December 12th, 2020. I am extremely pleased to have so many people here. We have a lot of folks coming back again. And today we're starting out with a presentation by Gary Stephenson. Gary's going to be talking about high-frequency gravitational waves, as well as some new data that he has that goes along with that. And then we'll do a Q&A session after that, and he'll be followed by Todd Desiato, who's going to be talking about quantum atomic resonance effects and how those might be leveraged for gravity modification. So again, welcome everyone. The APEC rules are we try and keep everyone muted at all times. Raise your hand. I mean, you can literally raise your hand. Raise your hand in chat. Entering questions in chat is a great way. If you have questions and you want to talk, and that just kind of helps us keep things organized. So without further ado, let me hand you over to Gary Stephenson, who has decades of experience working closely with Bob Baker, who was really one of the innovators that launched high-frequency gravity wave research. And Gary has done tons of his own research as well on this. Okay, so Gary, I am unmuting you now. Thank you, sir.
Thanks, Tim. It's a really pleasure to be here. I appreciate your invite. And let me share my screen too, so that it looks like you've disabled attendee screen sharing. So we'll need you to be able to enable that so I can share.
Yeah, sorry about that, Gary. And I'm just trying to find I have participants coming into the room at the same time, so.
Yeah, it's tough to stay on top of all that.
Okay. Let me see, share screen. It should, do you want to try and request sharing screen?
Yeah, I'm clicking on it. It says host disabled attendee screen sharing. I guess I could sign out and sign back in.
You know what? Why don't I try and do this? Or actually, who can? There we go. All participants. Okay. How's that?
It looks like it's letting me do it.
Thank you, sir. My apologies.
Oh, and I have a privacy issue. Let's see here. Yeah, we probably should have checked this beforehand.
Well, no worries. We've all had lots of little bugs and glitches with Zoom. So it's, you know, I'm surprised how well it works and how widely it's been adopted, though. I think this coronavirus has been a blessing in disguise for these conferences, to be honest.
Yeah, it's not letting me on this computer, so we may need to take a short break, and I'll get on a different computer.
Okay. Okay. Well, why don't I unmute? I'll unmute.
I'll be right back.
Okay.
Hello.
Yeah, I'll unmute Mark for just a moment. So I've got it on gallery view. So while we're waiting for Gary, Mark, and I'm sure this will only be a moment, but you guys have been doing research, and you were doing live broadcast last night, right? Can you tell me about that a little bit?
Oh yeah, so we had Jeremy Reese and Travis down at the lab, and we set up this really impromptu last-minute experiment. We're just doing a simple impulse into a superconductor, just to figure out how we would set up the high impulse experiments when we do it correctly. This was not a replication of Poklanov, but it was pretty cool how we got the cameras set up, and Travis was amazing there figuring all that out. We were using, I think it was webcams, and we just had to figure out how to move everything around. So it was pretty much a dry practice run, but it was very entertaining. I actually included the link to that video in the invite for APEC. It says click here. If you check out that video, it's pretty entertaining. It's not very scientific for this crowd, but it's entertaining for the masses, which is really where this needs to go, because this technology, the understanding of how this stuff works, needs to be understood by the masses. It needs to be understood by everyone in order to bring about anti-gravity disclosure. And that's what we hope to do, to bring more and more people into this field. This field is way too small as it is right now.
It sure is. I mean, the fact that all of us kind of know each other in this community is speaks to just how small it is.
And so one of the things that I've been doing is I've been taking the YouTube conferences, right, the playlists that we're creating, I'm putting those into the advanced propulsion channel in LinkedIn, and that's all propulsion engineers across the industry. So I've been broadcasting them in there. I started with last week's just because, I mean, you know, like what Paul, when Paul was presenting, that just struck me as the kind of thing they would just eat up, right? And then from there, it just got better and better and better. And I was like, okay, that's not going to freak anybody out. That's pretty relevant stuff. So I started with last week's, and then this week's, I'm hoping to do the same thing. So
that's awesome. Anything you can do to push the message, and really thank you, Tim. You've taken the reins on this APEC conference. And I'm watching your emails, and you're connecting with everybody and really doing a great job. Really, kudos to that.
Absolutely.
Well, thank you, sir.
Tim has done an incredible job. Incredible job. Couldn't have picked somebody better to do this.
Thank you. This has been a group effort, though. This has been a group effort. And, you know, I mean, again, it's...
And the presenters, with their incredible information, I mean, the stuff that's been said on APEC is historic.
Yeah, yeah. Well, and again, these are historic people. I mean, the folks that we've, I mean, Paul and Ron, I'm just looking at the list here. These guys are legends. Gary is a legend. You know, exactly. Rob Chambers is a legend who's hiding down there at the bottom. So, you know, and then we're meeting new people as well, right? So, and I think Jeremy is, as humble as he is kind of becoming a legend as well with his world's largest YouTube channel.
I know I have quite a big audience for this kind of stuff. We don't really get a large number of people super interested in this, but that's been my goal, is to, you know, make the education available to a wider audience of people, and also to embolden more people out there to bring them to, you know, out of the woodwork to come forward and present their information and their findings and their knowledge with us and with the group. And that's sort of my vision for what I'm trying to set up here. And of course, I wouldn't have been into this if it weren't for, you know, American Anti-Gravity and the research that you had done back in the day, and the people that I met through your website. So,
well, thank you. You know, it's also, it's interesting when you think about it, not just in terms of gravity, but doing scientific experiments live on YouTube is intriguing, right? I mean, like if you change the context of that, not just gravity, but like imagine that you were a geneticist or any other profession, right, that does experiments, to be able to unveil those experiments live on YouTube in real time, that seems like a true breakthrough, you know?
Yeah, we agree. And for us, it's fantastic because we can show by doing it live and letting people see what we're doing. It's going to be obvious we're ignorant to them, but not to us. And that gives people an opportunity to correct us and tell us how we're screwing it up so that we can do it right. That's invaluable.
And we got some great insights, actually. From that last live stream, we found out that gallium is not a very good binder or high temperature solder for the superconductors. So we're actually moving on to indium based on a comment in the super chat. And those little tidbits of information are really valuable for for actually making these experiments happen in a lab. And Jeremy Rich not only does, puts that all together, he also makes it entertaining. He knows how to fill in the empty spots. When not much is happening, and the audience, you're starting to lose audience. He pulls out his guitar and rocked that song. That was freaking awesome. We actually listened to that song last night. We just couldn't get enough of it. It was awesome.
I'm gonna start pre-writing those songs like ahead of time for our episodes and stuff. I want to make this like more entertaining for larger audiences and stuff. And also, but again, I want to keep it a little bit more serious and on a serious note too, because we do want to attract like more serious people. We don't want to be like a laugh. You know, we like to be human and have everyone be enjoying this and have a good time. You know. Okay,
so Gary is presenting. Let me mute everybody back out, and then let me mute everybody back out. I'll ask Gary to unmute. Or actually, yeah, there we go.
Can you hear me now,
Take
Tim?
it away.
Yeah, my apologies. I should have tested. My work computer doesn't like Zoom.
Yeah, well, go right ahead, Gary, and thank you yet again.
Yeah, can you see the screen? Okay.
Yeah.
Great. So when Tim asked me to do this, I put together a summary of the gravitational work I've done over the last couple of decades. And he was very polite when he got it, but he was like, you know, my people are kind of like more hardware people. You know, he didn't say, where's the beef? He was very polite about it. But could you add a little more hardware? So that's why I have hardware edition in here. I'm not a day-to-day researcher in gravitational work. My day job is aerospace systems engineer. But since getting my undergrad in physics, I've always maintained an interest in gravity. And so I've always tried to keep a toehold in the field. So I'm more of a gadfly or a spectator, but I do publish about once a year or so. So in my talk, I'll give a little timeline of the work I've done. I'll point out some highlights, but really what I want to focus on is what I think are still areas of interest that really haven't been explored as much as maybe they should be. And so I'll cover a couple different things. I've got a son that has the annoying thing of saying, is that a thing? Or that's not really a thing, is it? So these I think are things. These are things that we should be interested in. The first two kind of go together, thing one and thing two, detection of high frequency gravity waves and generation. Because if you have both those pieces and you have them in a lab, then you've got a gravitics lab. And you can test materials with that lab. And you can find out more about, are there index of refraction materials available for gravity? Clive Woods has written on that. Are there metamaterials that help amplify or help change the coupling between the stress energy tensor and the warp of space-time, the Ricci tensor? And Jacques Sarfatti says there are. But we won't know any of that without a gravitics lab that has a generator and a detector, so we can test these materials to see what the effects are. So I really want to advocate for that, and I really think those are things. The third thing I want to cover is a scalar field propulsion. There are a number of different techniques I want to really focus on Robert Forward's concept. And then I want to focus too on the TICTAC tech. What changes might be afoot if Jacques Sorfati is right about how TICTACs work and how that technology might really help with this other work. Then I'll polish my crystal ball at the end of this and give my predictions. The future is probability space, but I'll point out the things that I would love to see happen and see if we can tilt the tables in that direction. These are the first half of a list of my publications, and have a look through these. And if you see things that I haven't talked about that you want to talk about, feel free to throw them in the chat window. We can address them after the talk. I really only want to spend about 40 minutes on the talk and leave the rest of it for Q&A. The things I want to highlight here are the first International High Frequency Wave Gravity Workshop held by MITRE in McLean, Virginia in 2003. There was a second one that was hosted by EarthTech, Hal Pudhoff in Austin, Texas in 2007. And then there was a third one hosted by Fangyi Li at Chongqing University in China, 2017. So I like those workshops because when you get a lot of ideas together, a lot of engineers and scientists together, that's kind of when the magic happens. And so there's a lot of activity that went on surrounding those workshops, both going into and supporting those workshops, and then coming out of those workshops after we discussed them, papers that happened or discussions that happened that followed those up. And so I'll be alluding to those as we go through. The fourth one that I kind of wanted to highlight was this more recent one, Marcel Grossman 15, which happened in Rome, Italy in 2018. And this is where I presented a proposal for lab generation of a scalar field using a forward coil. And so I want to touch on, that's kind of theme 3. I wanted to touch on that a little bit too in this talk. Those are sort of the highlights. Thing 1, so first of all, why high gravity wave, why high frequency gravity wave? The advantage there is that when you're looking at producing gravity waves, it's a quadrupole. It's the third derivative of a quadrupole moment. Okay, so not only does mass have to be changing, but mass has to be changing in a way that has a third derivative. And if the mass energy distribution is changing in a way that has a third derivative, then your stress energy tensor has a third derivative, and that can change the shape of space-time, right? That's the other side of the equation, is space-time equals the stress energy tensor with a coupling constant. And so the higher the frequency, the easier it is to get a gravity wave. If you're looking at low frequency gravity waves, you need to crash 2 black holes into each other to see a signal. It's a little easier if you have a high frequency gravity wave, because a lot of the effects when you work through the math goes as frequency to the 4th power. So you're getting that to the 4th power effect, which is very helpful. In this particular, so I looked at a number of these detectors when I first wrote a paper for the very first high frequency gravity wave conference at McLean, Virginia in 2003. I went through a whole series of detectors, and the one I thought was going to be the most sensitive was this Feng-Yu Lee design. It's become known in the West as the Lee-Baker design because Bob Baker has been such a strong advocate for this detector as well. And in this depiction, which is out of Physical Review D, the high frequency gravity wave is coming in from the bottom. And it's situated so that the high frequency gravity wave is coming in longitudinally through a sensor beam. This is an electric field beam that it's an E field, essentially, static E field. And it's orthogonal to a static magnetic field. So you've got a B field, and then orthogonal to both those, kind of like a Lorentz force, like an E cross B, orthogonal to both those are perturbed photons. So you've got a lot of photons swimming around here, right? You've got the E field photons, you've got the B field photons, but when a high frequency gravity wave stretches that space-time in which these photons exist, it's perturbing some of those photons, and those perturbed photons go out in a symmetric way on a third axis. And so that's a huge benefit for when you're looking at a detection situation, because the detector on the plus x-axis might be noisy. The detector on the minus x-axis might be noisy. But when you see hits both here and here on 2 different detector sets, that's giving you a square root of 2 improvement in sensitivity, even for a stochastic signal. So that's a real nice detector orientation, and that is one of the reasons that everybody's been interested in that. The generic name for this kind of detector is 3-dimensional synchro resonance detector. There are other synchro resonance detectors. There's a 2-dimensional version called the Gershestein effect. This is a Russian that worked in the 60s, and he discovered that if you have the same arrangement and you run a gravitational wave in here, you get a synchro resonance set up where there's also going to be a signal, a photon signal that synchro resonates with the gravitational wave along the z-axis. The problem with that is it's in the same axis as the E field. So it's very difficult to measure that signal, and it's not nearly as sensitive. In fact, the Jasons in their review of the Gershestein effect said there's just no way it would work, in a terrestrial setting. This is a picture that came to us from Feng-Yu Lee of the same detector arrangement in the second high frequency gravity wave conference. It's interesting to see how this developed. At the first HFGW conference, it was a cartoon. By the second one, we'd clearly had more of a simulation scheme going on here. And then I don't have a picture of it, but in the third international high frequency gravity wave workshop, I saw, and I should have taken a picture of it because the paper hasn't been released, but I saw this same detector arrangement, only in a very detailed CAD version. So it looked to me like they had done a very solid, very detailed CAD layout of this same detector. So it seems to me that they've been doing quite a lot of work on developing this design. Here in this instantiation, I suspect this was probably for simulation. I don't recognize what the 3D modeling is here, but we're looking at a 10 watt, 10 gigahertz sense beam. So we'd be tuning the sense beam for the frequency of the gravity waves for which we're looking. So, and you'll also notice right down here at the bottom, it says HFRGW. What we're doing here is we're looking for relic gravity waves, high frequency relic gravity waves. The relic gravity waves would be gravity waves coming from the Big Bang. Apparently the Big Bang was quite a noisy event in gravitational space. So those are still ringing around. And it presents a noise floor, and is one of the reasons we haven't gone forward with using high frequency gravity waves for comm, because the comm signals we can make right now are drowned out by the cosmic relic gravity waves. So in this instantiation, this particular detector is going to be looking for cosmological or astronomical type signals. So it doesn't need a generator to be able to make measurements. It's looking for natural sources. But you can see then the B field, 9 Tesla for anybody who makes magnets and that's a pretty stout B field, right? But it is doable. You see B fields of that order in MRI machines, for instance. Microwave detectors run down to 480 millikelvin, very high vacuum. So we're shrinking the noise there by getting rid of atmospheric Brownian motion. And then the Gaussian beam is really only 10 watts. When I first looked at this detector, I was saying we need more like a megawatt. But the reason we don't is this focusing element. It's called a fractal membrane. It was added later to the design. And this is a focusing antenna, essentially, that will focus the detection photons onto the detectors. And this magnifies the effect quite greatly. And it makes it very, very much more sensitive when we use these fractal membranes. It's the same kind of antenna array. It's almost a metamaterial in a sense. Same kind of antenna array you might see in your cell phone. Notice that cell phones are flat. They used to have little antennas sticking out of them. They're flat now because the antenna is flat. It's a fractal membrane that's in your cell phone. And this is a similar kind of antenna. It's a flat, essentially phased array fractal membrane antenna that helps focus these detection photons. And so you get a huge magnification here, basically antenna gain because of that element. So this is my little hardware slide on how you might build one. And this is as far as really I have insight right now onto what the Chinese are doing on this detector design. I know that we're working with the high magnetization lab in China to get the green part of this built. I don't know how much their funding has happened since 2017, but in 2017, as I mentioned in Chongqing, they presented a very detailed design for this. Next part of this is lab generation of high frequency gravitational waves. And one of the schemes that historically has been looked at, Leonid Grishchik, who has passed since then, Grishchik and Sajin, his partner, both Russians, had schemed that you could use a toroid of resonating electromagnetic flux. So this is a pure energy toroid, and if you're going to use pure energy, it would have to be in the gigajoules per meter of resonating in a quadrupole moment. So you're kind of resonating like this, where you're squeezing the EM back and forth in a quadrupole moment, right? So you're compressing in this way and then compressing this way. And that creates that quadrature, quadrupole moment you need to propagate a gravitational wave. So you could use resonant energy that. So I took that idea and I said, well, what if instead of using E, we use E over C squared mass. So mass is C squared more likely to produce, mass movement is C squared more likely to produce a gravitational wave or more effective at producing a gravitational wave than energy. So if we can get plasma mass in a toroid, when I look at this donut, I think also of a tokamak. And can you get a tokamak resonating in that same pattern? They do resonate plasma all the time in order to stabilize it, and there are ways to do that. But as far as I know, it's never been attempted, at least not in an American tokamak. So here, back in 2003, you'll notice this is the Fang-Lee detector. It's a cartoon at this point. I was assuming a sense beam of megawatts, a B field strength of 30 Tesla, but it was 10 to the minus 33 strain sensitive instead to 10 to the minus 32, which is the current design. What is G wave amplitude? For those not schooled in the art, that's the amount of meters of change in a distance on an axis over the amount of meters. So 10 to the minus 33 meters of change in scale on an axis in 1 meter. Very, very small percentage-wise amount of metric change that's happening over a meter. But that's how they measure gravitational waves, is metric change over the metric. So that's on either axis. And as the gravitational wave propagates in transverse direction, the wave, and I think I have a video I can show that kind of shows this. The wave is shrinking and expanding space-time in alternating directions in a way that preserves momentum. The reason you can't have a regular sine wave, transverse wave in gravity is it doesn't preserve momentum. So the only way you can propagate a gravitational wave is in a way that preserves momentum, such as a quadrupole, octupole, or higher order. The very interesting thing about the last detection at LIGO was because the mass sizes were so mismatched, we saw very high order gravitational waves. They weren't just quadrupoles, they were octupoles, 16 poles, 32 poles. So kind of astonishing that we were able to see these higher order effects. All the designs I'm talking about are for quadrupoles, the lowest order effect. Here we see the inside of an example tokamak. This is the D3D, General Atomics tokamak in San Diego. The Department of Energy uses this to experiment with new instrumentation. This is the best and most fully instrumented plasma experiment in the world. If they're working with sensors for plasmas, they test them out here first, and then they put them in ITAR second. So this is kind of our contribution to ITER, is testing these various plasma sensing schemes. This is one thing we could play with, since it's an experimental fusion tokamak, and try to repurpose it. The good news about tokamaks is they're already built. You're not starting from scratch. The bad news is they weren't built for this. They were built for making burning plasma. And so we would need to repurpose it. What would we need? We would for sure need these microwave excitation coils. So we're vibrating in a quadrupole way at microwave energies, enough plasma that we can make a gravity wave big enough that we can sense it. And if we're making that much microwaves, we're going to need shielding. We're also, because plasma sensors aren't used to operating at the kind of bandwidths and frequencies we're talking about, we would need upgrades to the plasma sensors. And then because these devices, the schematic of it, this is a simplified schematic of it. If you've ever looked at a fusion tokamak, they're a mess. They are complicated. There's not a lot of geometry room. It's pretty crowded. So we would need physical updates to move everything else out of the way of the things we want to add in. So there'd be a lot of changes to this, but you can see, inside here, it is a big device. There should be enough room to accommodate some of these changes, in terms of excitation coils. So there's some ideas. We would also want to accommodate the high frequency gravity wave detector somewhere, probably immediately above, immediately below, or both, immediately above and below, to make sure we're really picking up a real signal. And that would be then a gravitics lab, right? Because we've got now a generator in close proximity with a sensor, as I showed here. And the other thing is we could put then samples of materials between this generator and this detector to say, hey, what does a metamaterial do for us? what does a superconductor do for this? I alluded before that Clive Woods, one of my associates that I've co-authored with in the past, has written papers about superconductors being able to focus gravitational waves. It is because they have an index of refraction in the gravitational permittivity. If that's true, that would be an enormous benefit, right? Because you could take then a big generator, focus the energy, and make a much stronger signal. There are some other ways to generate. So I think we can see if we can get this animation working. I'll have to access the web, and we'll see if we can get this going. And I hope you can hear the audio.
The first gravitational wave generator option uses micro-electromechanical system actuators for impulse generation. Known bulk acoustic resonators are triggered to jerk in unison. They are aggregated in two arrays represented here as blue squares, generating gravitational waves on the focal point at the axis of rotation. At the focal point, we see the characteristic distribution pattern predicted by general relativity, with the oscillating red squares representing the oscillations of space-time that constitute gravitational waves. The detector accepts the gravitational wave along an axis stimulated by EM and immersed in a magnetic field, emitting detection photons perpendicular to the axis of travel. The next gravitational wave generator option uses X-ray lasers for impulse generation. Each X-ray laser fires a short, strong X-ray pulse, which impacts the X-ray target to create a third derivative of motion needed for the generation of gravitational waves. A pair of X-ray lasers is used in unison to develop the gravitational waves at the central focal point. Gravitational waves are again represented as red boxes, with X and Y axes of the metric taking turns stretching and shrinking. The same detector is shown in this case, with the signal photon triggering a sensitive quantum detector to register an output signal. A frequency time standard is a possible early application. A single gravitational wave generator could be used to time synchronize any number of remote detectors, even those in orbit. The detection leading edge can be very tightly controlled, as gravitational waves always follow geodesics and are relatively insensitive to index variations and interference sources. For more information on gravitational wave products, contact Seculine Consulting.
My thanks to my cousin Catlin for producing that video very inexpensively, because she was just hanging out before she got her lynda.com job on training videos, and so I got a really good deal on it. Okay, the third thing I want to discuss is production of a scalar gravitational field. This is cut from a paper I presented at Marcel Grossman. General Relativity Conference is given every 2 years essentially for mostly theoretical physicists, but they also do present LIGO results and experimental results at the same conference. So it was a good conference to go to get critical feedback, and I really appreciated them allowing me to present such a far-fetched design to a group of really august physicists. This was a paper, it was based on a paper by Forward in 1962, in which he knew at the time there wasn't going to be a technology that could support this design. But it's based on the Lenz-Thurring effect, where if you have mass flow running around this toroid and it's inspiraling, the frame dragging tends to concentrate more on the inside than on the outside. And that's purely geometry. It's because there's less room on the inside of a toroid than there is on the outside of a toroid. And you could wind it even more tightly so there's very little room on the inside, and really strengthen that scalar field, acceleration field that's developed on the inside. You can imagine a craft too that is sized so that there's very little skin of the craft on the outside of the coil. So there's no downward or very little downward force happening because of this lens throwing effect on the outside, even though essentially the lines of gravitational flux are the same on the outside and the inside, but that the vast majority of the mass of the craft is occupying the inside of the coil, not the outside of the coil. So this is one design for, how do we make our own flying saucer or saucer-shaped craft? Unfortunately, using current technology, there's no way to get it off the ground. You can't make 1G with current technology. If you do the numbers here, and Ford's equation for this toroidal development of gravitational force depends upon the derivative of the stress energy tensor, the radius, the internal radius, cross-sectional radius, as long as the outer radius of the toroid, and n is the number of turns. So if you get a nanowire going that carries a superconducting nanowire that carries a lot of currents, this could be measurable. And that was the premise of my paper. It could be measurable in a laboratory setting with a 10-meter device. This scaling factor, a gravitomagnetic permeability, isn't the scaling factor you see very often. It's essentially the coupling constant between the stress energy tensor and the space-time the space-time warp. So this is you can factor this into the g over c to the fourth typical term, which is n sub 0, and n sub r. It depends upon what the mass is in here, and we don't know what mu sub r's are. They're eta sub r's. We don't know what this value is, and that's one of the reasons to have a gravitics lab, is to be able to measure that, because that will impact the effectiveness of our device potentially very substantially. Now, I'll go over in a second how Jack Sarfatti has looked at metamaterials that can affect this in a very large way, or even in a negative way, for essentially inverse gravity, right? Repulsive gravity instead of attractive gravity. If you can get a negative index material, you can get repulsive gravity. So that's what I presented at Marcel Grossman. When I actually read this paper decades ago, but when I had been studying for energy storage, superconducting magnetic energy storage devices, they started looking like this to me. And so this looks like high-powered superconducting magnetic energy storage, or SMES device. These SMES devices have been under development by the DOE. There was a program before the Trump administration at Brookhaven to build one of these. I don't know if it was Obama or Trump that canceled the program, but it's now been mothballed. But certainly that could be restarted at Brookhaven. It would be very interesting to see not just whether they could make a good size SMAS, but whether they could use it for gravitational wave generation. So the other thing to keep in mind here is that SMAS, you want a core that's high permeability for SMAS, because you're storing energy in the magnetic field. But for this application, you don't want that, because the more current you have, the larger the magnetic field, and you start getting Lorentz forces that start trying to rip apart the machine. So it's better actually to have a vacuum or an air core for an SMES that's being used for gravitational waves. And then where you put your material, your effective material that concentrates the lines of flux, would be in the center of the toroid. This is completely different than electronics, right? Because this isn't where the electrical field is. The electrical field is on the inside of the torus, but the gravitomagnetic field is in the middle of the torus. That's something to bear in mind when you're using these things. How to build one? I have a lot of gory details. There's two versions of this paper. I have a lot of gory details, not in the Marcel Grossman version, which is a 7-page version. I have another 20 or 21-page version that was published in 2019 that has all these build details. Marcel Grossman limited my page count to 7 pages. So it didn't have the design details. but I also published in a Chinese journal, the gory detailed one that has the extra 14 pages of design details. So I can recommend that 2019 paper to you. And the link is in my list of publications at the beginning of the talk. So that's the scalar part. Now imagine using that same coil, but in a segmented way. Here I show the segments. For instance, you can cut this into 16 segments, build those segments separately, and then connect them together later on if you've got superconducting connectors, which are tough to come by right now. But presumably you could do this in segments. If you do this in segments and don't connect them together and energize them independently, you can energize them in quadrature such that you are not necessarily operating them all on the in-spiraling direction, but some of them in-spiraling and some of them out-spiraling, such as you're doing a quadrature. And if you get that, and you're able to sinusoidally inverse that quadrature current, so you've got a sinusoid that's, these two are in phase, these two are out of phase, then you can get that third derivative of a quadrupole moment, and you can get a gravitational wave distribution that looks kind of like this pattern. So you can get gravitational field pattern in a snapshot in time that looks like this pattern, but alternates up and down and back and forth. And that pattern will help create a gravitational wave. This might be an easier way to build a generator than either the generators shown in the animation or a generator using a tokamak. So this is yet a fourth way here to generate gravitational waves. By the way, since that publication came out, the two generations in that animation, the second one, the X-ray laser one, has come under criticism because there's no material that will stand up to the impulse force of an X-ray laser that will be able to maintain its integrity in mass enough to jerk in a sharp enough way to create a gravitational wave. So I think the X-ray laser one is probably not going to work. The MEMS devices, you would need a field like an acre of SMEMS devices to be able to make the SMEMS, sorry, the MEMS device work. Okay, that brings me to the fourth part of my paper on TICTAC technology. TICTAC is a euphemism for those not familiar with it, that is used as a nickname for, some call them UFOs, some call them UAPs, a UFO, unidentified flying object, UAPs, unexplained aerial phenomena. The reason people don't like the term UFO is we're not even sure if they're objects. We could be looking at a wormhole or a hole in space-time, which isn't really an object per se. And it doesn't look like it's flying, right? It doesn't look like it needs aerodynamics. In fact, quite the opposite. These devices tend to ignore aerodynamics. So it's not really flying per se. So that's why the more modern term is unexplained aerial phenomena. I don't want to get hung up on technology. Whatever you want to call it, it was tracked by an F-18 using an advanced targeting FLIR. This is a pod that's used for sensing and tracking and targeting of other aircraft. And those pods were mounted on, sadly, unarmed F-18s. It would have been very interesting to pop a shot off. They were unarmed and had only these pods because they were set up for training missions. They deployed off the USS Nimitz in 2004. This was discussed by Hal Puthoff in a 2018 talk, which I'll show a link here. I'll just give a very brief discussion on why this was an interesting sighting. Two reasons, really. First is this AT FLIR formed a track on it. It has a low light level camera and also an infrared camera in it. Both of those were able to form a track. The laser designator was not able to get a return. So for whatever reason, light doesn't bounce off of this thing. But as a black hole in space, 2 out of the 3 systems were able to form a track on it. So we knew we weren't just looking at phenomenology or swamp gas. This was a real thing. The first important thing. Second important thing is we discuss intent. As discussed, I don't know how much Hal goes into it. I know I have a talk later that's linked that's come out very recently last week, in which the the Milburn report was being discussed, and they talked about some of the deployment activities of these F-18s. And one of the deployment activities was they had to rendezvous at a cap point. I believe that stands for combat assembly point or something like that. And it's a point at which all the aircraft had to rendezvous. And when the order was given to rendezvous at the cap point, the UFO moved to the cap point at a very great acceleration before any of the aircraft had a chance to react, which clearly shows intent. So we have, number one, it's a real object. Number two, we have intent. That's what made this sighting so alarming, and that's what really set off the Joint Chiefs of Staff. And they absolutely had a cow over this. And they decided, hey, we've got to get this out here, and we've got to figure out what's going on with this device. And I'm sure there was an internal investigation to make sure we weren't shooting ourselves in the foot. But it's beyond belief to me that some DOE-Q program or some dark DOD program would intentionally interfere with a military operation and put their aircraft in the way of a combat assembly point. It's impossible to conceive, because whoever would have given that order would have been drawn and cornered and had the pieces shot for treason by the Joint Chiefs. So it's not one of ours, is what I'm trying to say. It's also inconceivable that the Chinese or Russians would have this type of technology and not use it to invade Crimea and not use it to invade Taiwan, right? They have too many military objectives. It would be too easy to take care of if they had this technology. So all of the fairy tales we've been telling ourselves about might be one of our dark programs, or it might be foreign tech. It just, for this particular scenario, all of those arguments lost plausibility. So that's what made it especially fascinating, and for the Joint Chiefs especially troubling. So there was a move afoot to release this more widely, to try to get input and ideas on just what the heck is going on. It was released to the History Channel, the footage, and so I have a picture of that here. What got my attention was last November, I subscribed to Aerospace America, because I'm a member of AIAA, and this was their cover story. Typically, UFOs don't make the cover of AIAA, right? This is the most credible journal that there is in the United States for aerospace. So that caught my attention. Jack Sarfatti has theorized, he has been working for HAL for many years on unexplained aerial phenomena. He has theorized, based on some of the phenomenology, that the skin of these UAPs are metamaterials, and I'll show in the next slide why he believes that. And you can imagine too, I won't say this is how TICTACs work. I'll say if I had to build one, this is how they would work. I would use forward coils for the up, down, forward, back, left, right kind of motions. And perhaps I might like to use metamaterials to strengthen the effects of those forward coils. But here's something else I want to propose to you, and it wouldn't necessarily have to be a forward coil. If it was a smart skin, you might be able to do the same thing. Who's heard of the Lenz's law? Lenz's law says, if you have a magnetic field, thank you, I see some hands. If you have a magnetic field, a magnetic field, and you have something that you can create a current in, that the current that you're creating will oppose that magnetic field. And you can actually levitate devices this way. I saw a very impressive demonstration of this with an aluminum platter. It wasn't a magnetic material, it wasn't ferromagnetic. It was an aluminum platter that had current that was being developed in it by a magnetic field. And it literally, probably a 10-pound platter, lifted off a table-size coil. That's Lenz's law in action. Now, the question is there a Lenz's law for gravitomagnetics? In other words, if you have a forward coil capable of maintaining enough current in it, then it can generate 1 G of backwards countercurrent. Can you have such a forward coil? Let's see if I can do this without flipping the page. Such as this one, inside the craft or on the skin of the craft, to make Jack happy. That amount of current, that amount of countercurrent could be actually induced by the gravitational field of the Earth. If that's the case, then you don't need any power at all. It just starts floating. And that is somewhat consistent with some of the stories you hear, right, about these craft. It just floats there. It doesn't need any power, doesn't need any input power, because its input power is provided by the gravitational field of the Earth itself. Furthermore, you could have a secondary forward coil that could be charged up with current using the charge, gravitational charge of the Earth. And you've got that induced current now, and you use that induced current as a power source for all your other forward coils that are also powering the craft. In other words, you don't need any other power. If you're in a strong gravitational field, it powers the craft all by itself. So that is something I wanted to raise up. I put that in the very last chart of my Marcel Grossman talk. It wasn't in the paper, it was in the chart set. And I got blank stares. I don't know that the physicists in the audience either knew Lenz's law or knew what to make of it, but I wanted to raise it up to you all here too, because I feel like you've got a lot of open minds here, and we'll see what happens if we can build one that can actually get up to 1G. But if we can, and we close loop it, in other words, we just short it out, so it's all one continuous coil, will it charge up? It'd be very interesting to find out. A little more on Jack. Who is Jack Sarfatti? He's a friend of Hal Puthoff's, who has been a researcher in this field for many years. If you don't even know who Hal Puthoff is, I'm not sure we can be friends. He has been working in this field for, well, twice as long as I have, at least, through SRI first, Stanford Research Institute, and then now he has EarthTech, his own storefront in Austin, Texas. There was a now famous talk given only a few months ago by Jack Sorfati at the Estes Park lecture. Estes Park is held every couple of years. It's named after the place it's held in Colorado, but it's sponsored by some O'Neillians. I forget the name of the institute that sponsors it. But these O'Neillians are basically space fans. And so they're good enough to use some of their resources to sponsor this conference every couple of years on advanced propulsion techniques. So Jack went to one of these. Jack is one of those guys that doesn't quite settle down long enough to publish anything, but he has a lot of good ideas, and his talks are quite interesting. And so one of his talks, he was talking about the incompleteness of Einstein's field equation. So this is Einstein's field equation in blue, with the exception of the S. The S is new. That was Sorfati named it after himself. But here you have the curvature of space-time on the left, and you have the organization of matter and energy on the right, and the scaling constant g over c to the fourth. And what this says is mass and energy in the universe give the universe its shape, give space-time its shape. In other words, the curvature of space-time is affected by mass and energy in very simple fundamental terms. And there's this very stiff scaling constant that says it takes a lot of mass and energy to get a little bit of curvature in space and time, either tensor curvature or scalar curvature. So how can we improve the situation? Well, what Sarfati's breakthrough is he said, this is a great equation for point masses. This describes the universe for point masses, where masses are all at a point. And geometrically and mathematically, it's easiest to treat them like points, because it's as if you concentrated all the mass in a point. The problem with that is you're never actually in the matter. If you're actually in matter, then the equation is not valid, because the equation assumes the speed of light never changes. And of course, we know, because of the index of materials, the speed of light does change. And so the coupling constant probably changes too. Why? Because gravity, scalar gravity, and gravitational waves all propagate at the speed of light. So if that's true, and you believe that, then you can write a zero-rank tensor called S that takes that into account. That takes material scaling due to the presence of matter into account. And if it behaves at all like light in an isotropic material, S will look like this. Now, this is permittivity and permeability, just plain old permittivity and permeability. Here's what Jack wrote. So index of material, N, is E and mu to the square root, right? That's index of refraction, essentially. So look at S. If you plug in N here, S is N to the 4th power over mu squared. Holy cow. If you have a high mix material, you can get a 4th power effect. I mean, that's just huge, right? So say you have, now you are dividing by mu squared. So if you have high permeability material, you're only getting mu squared because it's mu to the 4th over mu squared. However, if you have high permittivity material, like a supercapacitor that has 10 to the 8th permittivity, now you've got an enormous effect. So 10 to the 8th to the 4th times 24. So the effects due to asymmetric capacitors, the effects because of superconductors, amplifying the effect of a gravitational impulse. Now you see directly where it's coming from. It's a direct formulation. And so now if we have a gravitics lab, we can start experimenting with these materials. We can prove that this S matrix, even for isotropic materials, we're not even talking metamaterials yet. These are just vanilla isotropic materials. We can prove the gravitational effects of these materials. And now instead of me needing billions of miles of superconducting nanowires, I can knock that 10 to the 9th down, another 10 to the 2nd, and even then my effect is 10 to the 12th bigger. So we're gonna have a very small device now, a very small forward coil, making a very large impact if we have these isotropic materials embedded in the core of those forward coils. That is why I wanted to bring up Sarfatti's work. This is just a little more detail on how did he get here. He got here because we saw in some of the footage what looked like phase shift. Phase shift in terms of light, which implied phase shift gravitationally. So Jack pulled out of this S term, this phase shift term. These two are still getting multiplied together, but also multiplied in here, a cosine of phase shift, where he's defining the phase shift this way through the tangent. So it's the arctangent of this thing over here is your phase shift. And he's saying that it's negative for repulsor over antigravity, which we saw at the tail, which means the TICTAC being pushed away. And in the nose of the TICTAC, we saw an attractive or positive phase shift where it tends to be going forward. So it based on the phenomenology, the TICTAC appears to be using phase shift, which means gravitational redshift and blue shift. And so I think that's where Jack got this formulation. He was trying to formulate it in a way that the TICTAC was using it and then would describe the TICTAC. By the way, the Nimitz is not the only sighting of these things. The Roosevelt sighting was a little bit clear. I don't know that all the details of the Roosevelt sighting have been released yet, but it tended to confirm the shape of these devices, which is cylindrical with hemispherical ends, hence the name TICTAC, just from geometry. So far I haven't gotten anywhere. I haven't got any experiments that have done any good. I've studied a lot of things. I've kissed a lot of frogs. Nothing's turned out so far. But I think we're getting a lot closer now with this S matrix. I feel like if we went back to some of these ideas, we could potentially get them to work. Or other investigators, such as some of them on the call, using other gravitational experimental techniques, using some of these either metamaterials or high permeability or high permittivity materials, could potentially confirm some of that. What I would like to see more of is true funded programs for the 3D SR 3D synchro resonance detector, a plasma tokamak or some other generator, maybe a segmented forward coil generator, and a real program for gravitomagnetic toroid scalar generation program. We could see, can we do this at least in a lab? I think that'd be something that would have a lot of value and help placate the public as to say, we're doing something. If we do 1 and 2 together, we already have a gravitics lab because we have a generator and we have a detector. So we know when we're changing the environment, we're seeing, how does this impact? And then, as I pointed out just a moment ago, Sorfati has this S term. We could really look at that S term and decide, is that a thing? On the TICTACs, there's a really good. It's long. It's not boring. a really good walkthrough of the Milburn report that came out that was funded by the Israelis, that was done by the Brits on basically the US UAP task force program. That's on a YouTube. I'll give you guys the link to this. And I'll post this. I can send this to Tim after the talk because I don't think the old version of my talk had this link, because this link just literally came out days ago. But I think once you look through that, you'll be convinced too that this phenomenology is real. We don't know where it comes from or what it is, but it's certainly real. My opinion only, I don't know. I don't have a DOE Q clearance, but I think we're not doing enough. At least, if not nothing, not anything visible. I think as Scott Fitzgerald said it best, the strongest guards are placed at the gateway of nothing. It's the condition of emptiness that's so too shameful to be divulged. I think we're protecting this because we're not doing anything. And I think that's kind of too bad, because we could be doing quite a bit here. And I'm nothing against hobbyists. I'm a hobbyist myself. But why isn't the US government, doing more with gravitics work? Honestly, this is a little embarrassing. So I don't work for Battelle. I don't speak for them. I don't work for GOE. But honestly, we should have seen more after the last 50 years here. That is all I have. So I guess I'll stop sharing. And Tim, if you want to open up to questions, either through the chat window or means, I'm happy to take questions.
Gary, thank you so much. This was amazing. So let me do this before we do questions. Let me invite everybody to unmute, and we're going to give you a big round of applause. So ask all to unmute, and let's give Gary an enormous applause, everyone. Okay, so let me here. Okay, sorry about that, the mute button. Let me see, Jeremiah has been jumping up and down literally for about half an hour. So Jeremiah, let me let you go first, sir.
I've been really excited about what Gary's presenting here. He's talking about how the space-time curl can effectively pinch or squeeze the gravity wave, and it produces photons that we can detect. I mean, that's incredible. The linking between an electromagnetic field, or just a fixed magnetic field, and an incoming gravity wave that traverses through that field, and the idea that it produces a signal that we can then detect, it really draws a solid link between electromagnetism and gravity, which is, of course, that big unifying factor that we've all been searching for, that physics has been dreaming of fixing forever. So this gives us a really functional way to look for if our devices are actually producing any kind of gravitational waves, because it's a mechanism. And it's very simple in your setup. You just have a really strong field. So one of my big questions for you, Gary, was in your system, you use a 9 Tesla field, an incredibly strong field. And I'm guessing that's just to get your noise floor low enough to the point where you can detect?
Yeah, it's a function of the magnetic field strength. It's a function of the sense beam strength. And so the weaker the signal, the higher the B field has to be. So you can imagine if your signal's not 10 to the minus 32, but 10 to the minus 20, now you can divide that magnetic field by that many orders of magnitude and get the same effect. So it really does scale that way.
That's incredible.
Another issue I was thinking, with 9 Tesla and you're dealing with stainless steel, that will like destroy the vacuum chamber, wouldn't it?
Yeah, it'll warp your vacuum chamber. Yeah, so you really have to be careful. What are you going to make your vacuum chamber out of? And it may be composites.
I mean, I don't know about titanium. Might be a better choice. We do have a stainless steel vacuum chamber over here. We do have superconductors and 10 gigahertz signal generators. We could push 20 watts with our traveling wave tube amplifier, and I think we have pretty much all the components except for that layer that you're talking about. The
fractal membrane. Yeah, you can design that. You can etch that on a PCB. So I don't think it's that tough. It's that tough to design. I think what you have to do is spy a little bit on the cell phone companies, because it's very proprietary, these fractal membrane designs. You can find research papers on it, and probably it's easier to find a higher frequency microwave one than it is cell phone frequencies.
I mean, PCBs are cheap to order, right, Gary? We can order a set of PCBs for basically like $20 now online. So
sure, if you have the etch pattern, you can send them to a PCB house and have them etched for you.
Yeah, that's amazing. Would you be interested in maybe working with us a little bit to try to replicate some of these things? Is that
I am not a fractal membrane expert, but I could certainly point you to some research articles I've collected over the years.
Not just on fractal membranes, Gary, but you're obviously a genius. And you know,
sure, yeah, we can work offline if you want me to help consult.
Yeah, I mean, we want to build based on all the stuff that's in your brain, because there's definitely a lot going on there, and you presented some really fantastic and important things that have huge implications in the experiments that we're doing right now. So
I have a few spirit clock cycles every week, so I don't know how much I can help you guys, but I'd be happy to get with you offline.
Also, our investor or donor actually offered, like, if anybody has relevant information, he'll fly them out here and pay for all expenses to come down to the lab and actually work with us live on these experiments.
Yeah, that'd be fun to do once the COVID thing's over, which seems like months, not years now. So sure.
If anybody's brave enough to traverse the COVID environment, I mean, the availability to come out and help out at the lab is there. It's an open offer, basically. So
it's awesome.
Anyone's interested in helping, and especially, I mean, we want to work with you, Gary. You're brilliant. I love the information you present. I'm very excited about it.
We even rented a guest house for any visiting scientists. Jeremy and Trav were in it the other day, and we have pretty much all the components that you were talking about. We got 18.5 gauge wire.
Yeah, I love poking around labs. I'm myself, so I would love to come out and poke around sometime.
Yeah, I was thinking of powering the 9 Tesla field using the hybrid batteries. This is primarily a hybrid battery shop. This is the back of a hybrid battery shop. So we could use those are very good at very high impulse energy. So we could probably get to 9 Tesla. But I would be afraid of what would happen to that, stainless steel. Or
the cat version I saw of that detector later on looked more like a diving bell, pressure vessel than it did an ordinary vacuum chamber. So
that makes a lot of sense.
And it looks not made out of steel. You can't make a stainless steel.
I mean, as long as you structure it and you make sure you make that. So technically, I mean, the magnetic field just needs to be present where the gravitational waves are traveling through, right? So you could
just the core.
You have a very tight field with a closed external loop. So
that's right. So it's just in the sensing core itself. Yeah.
So could we then use a yoke to effectively focus it and remove the external forces on the stainless steel walls of the chamber?
Sure, potentially. Mm-hmm.
Okay, awesome. We just need to find some really good materials to build a yoke out of then. And perhaps very, very pure iron, because if you guys have looked at the response of materials in magnetic field, very, very pure iron. The more pure you get it, even by the fraction of a percentage, actually increases the maximum saturation of that material and gives us a huge area to work with.
Would these are about 1 inch YCBOs. Would this work?
1 inch by about ½ inch thick. Probably not going to get any of that. Hey,
I can't off the top of my head speak to that. It depends on the index of the material, but those are probably very high index. That's a very high index material, probably.
They came from the Czech Republic.
They're a bit hard to pin. We don't know for sure if they're going to work for the Pakhanov replication, because according to Porer's papers, Pakhanov had cracks in his superconductors, which caused him serious problems. And these definitely do show some signs that where they were cast, there are some cracks that may be deeper within the structure than we can investigate. So they may not, in fact, work for Pakhanov's impulse discharge. But the idea that a B cross B can warp spacetime is going to be critical for us to understand how to build this thing. There's always that bilayer mystery. And I just sent you, Tim, email this a little bit earlier about Porer's stuff and how he talks about using Josephson junctions in his superconducting emitters. And that's his big key. So that would be basically Pakhanov's bilayer to produce one large Josephson junction compared to millions of them within the structure to produce gravitational waves.
Well, so Jeremiah, let me ask around a little bit and see if anybody else has questions. It looks like so.
Thanks. Sorry.
Oh, no worries. Okay. Oh, let me see. Mr. Murad has a question, sir. And I need to okay.
Can you hear me, Gary? It's good seeing you.
Yeah, likewise, Paul. Hi.
All right. Regarding MRIs, they have 1.5, 3, and 10 Teslas. So to work with 10 Teslas isn't that big a problem. The comments that you made that I'd like to, I guess, make some suggestions is that, well, the US government guys, probably no one's interested in high frequency gravity waves because they don't understand technology. And if you haven't got somebody to bless, it goes nowhere. Now, I don't know if Sal Pace will be the guy to talk to about that, but that might be an approach. And, you know, Frank Mead is gone. Now, regarding the AIAA article, the articles itself was kind of skeptical. Never did say anything like, hey, it's an alien vehicle. We just don't know. We don't know. And I had gotten involved in about 2 weeks of arguments on AIAA Engage about UFOs. And the bottom line there was that, yeah, it's an article, but we don't believe it. And, you know, like, bingo, none of this means anything. So you take that with a grain of salt. Regarding the Sarfatti comment, the physicist doing this normally says C is equal to 1, H is equal to 1, and so on. And everything looks great.
At all to actual units the engineers use,
But you looked at that equation, and it's 1 over C to the 4th. And to get over C to the 4th, that's a lot of power. And, you know, I remember a conversation that Eric Davis said that you may bend the curvature of the space-time continuum with a nuclear explosion. And he's probably right. It's just tough to get to that C to the 4th.
That energy level, That's why we went to the high frequency, right, to try to help with that situation, because then you've got the stress energy metric changing fast enough that derivative helps increase the effect.
Well, you didn't show Baker's comment about that 1 to the C to the 4th anyway in gravitational wave detection. So you have the same problem as what you're seeing with the way Sorfatti's working the problem.
Yeah, it's a lot to overcome that C to the 4th.
Okay, that's all I had to say.
Okay, so let me thank you, Paul, and then let me see who else has questions. Jeremy Reese had asked. He was wondering if you could use laser etched metals instead of nanowires. And Jeremy just left. Okay, so
but potentially, yes, you can etch the wires. That is one way to make the wires. I like superconducting wires because they carry more current. More current means more electrons. More electrons cycling means more change in the stress energy tensor.
Okay, and let me see. He's in the room. I think he's just focused on something else. Let me see. And does anyone else have questions for me? Just raise your hand if you'd like, or you enter them in chat.
Jeremiah here.
Yeah, I've got a question for Gary. What we found out from the last APEC conference from Richard Van Durk was about the extremely high electron drift velocity in new materials like graphene nanolayer films or stacked graphene films. Could these potentially be a room temperature solution to maybe building a non-cryogenic gravity wave detector?
Yeah, potentially. The currents are a lot lower than superconductors. So I really like the high currents of superconductors. But if they can either get their the current density up, or if these nanowires can get the critical temperature up, either approach would be good. It would really be nice to get these nanowires to operate at refrigerable temperatures, so you can put it in a refrigerator instead of a Dewar.
Yeah, I mean, I think right now, seeing as this is the an engineering conference, this is a challenge of engineering to figure out how to make these materials so that we can produce gravitational wave detectors and gravitational wave generators that operate at room temperatures without special cryo systems. I do think it's possible, and Ben Nurk pretty much proves that he can.
And it may be. I'm not looking for the right current source. One of the reasons I use the nanowires is because the person that urged me into presenting this paper was William Riken, who is a nanowire researcher in Japan. And he had some material, he doesn't know what to do with it. It's like, it doesn't need to be this good for transformers. I mean, it's 30 nanometer wire that carries 200 amps. It's like,
that
is this for? I'm like, well, I can think of S-mass, number one, and number two, I can think of forward coil.
I think we could all, I think every lab on this conference could probably use some of that in their lab, yeah.
I mean, we have everything needed to put
strong magnets, right? Electromagnets.
Yeah, we could create crazy strong electromagnets over here. We have nickel batteries.
Right now it has to be in a Dewar that's 220 Kelvin at least, if not 200 Kelvin. So critical temperature, he can't really get it above 200, 220 right now. That's his limit.
That's something that I think we can actually develop and work through on the engineering side. I think we have what we need now in technology to be able
thermoelectric cooling comes pretty close if you're looking at cooling tech.
Yeah, forward stack can get down pretty low.
Once you're in a vacuum chamber, the superconductor maintains its temperature pretty well. And we actually have a mechanism to keep the superconductor cool using a
contact surface probe.
Yeah, like a contact surface probe. So once we get the superconductor at its critical temperature in its pinned form, we can put the probe in there inside the vacuum chamber and keep it cool.
The other nice thing about his material is, not to get too far off of gravity, but his material is slow quench. We don't quite know why, maybe flux spinning, but for whatever reason, it's very slow quench. So if it does reach its critical temperature, it doesn't quench instantaneously. It doesn't explode, which is nice from a safety point of view.
Hey, welcome, Richard Ben Durek.
I am so glad to see you here.
Oh, yeah, thanks. It took me a while to get over here.
I've been talking about you since you haven't been here.
Hopefully it was something good, not bad.
It was all praise.
Oh, okay, thanks.
For replicating your experiments. Very excited.
All right, thanks.
This month is doing that.
All right. Well, I just wanted to see, what's going on now. Are you guys still in the middle of this gravity wave presentation?
We're in questions and answers at this point.
Okay.
Jeremy, how's the live stream going?
Guys, we have 120 people, 117 right now viewing.
Are there any questions from the audience?
Yes, Gary Chase wanted to ask about the effect of HFGW to induce dipoles in the particle-antiparticle pairs in the vacuum, such as electron-positron pairs. And and then I have a second
strong enough. It's a very weak effect, so it probably wouldn't be strong enough to do anything like that. For that, you need pretty extreme fields and situations.
Right, in order to break that Schwinger limit. What is Gary's awareness of induced dipoles in electron-positron pairs in the vacuum in response to HFGW?
Yeah, I need a black hole to do that.
Yeah. So I had a question about what I wanted to ask you in relation to some of the materials about metamaterials and ways to. So the nanowires is kind of an expensive way, and I wanted to point to some research that I came across recently in Sci News. And I'll send the link in the main chat right now. And that was a team that was at University of Rochester, I believe, and they're working with laser etched metals, and they're able to create
and plasmatrons and polaritons. Okay.
Yeah, the polaritons, the surface plasmon polaritons, and they're able to create these types of metamaterials using just laser etchings on metal. They etch like a grid pattern or a lattice onto a metal, and that actually produces a metamaterial.
Nice. Well, that could be the kind of skin that we need to make a craft like this operate. So
yeah, this is definitely some research I'm hot on, and I just wonder how accurate this needs to be to laser etch these metals. But anyways, I was curious if you'd heard of that, because you had brought that up too, and
this is brand new. The whole using these metamaterials to help affect gravity is brand new to me. I think it was mid to late September when Jack first presented that, and it was brought to my attention. And when I reviewed it, I thought he really did have something, and so I had been communicating with him off and on it. But I haven't gone into detail on exactly what metamaterials could be useful here. Until now, my only exposure to metamaterials was for like stealth technology where you're talking about creating a negative index at radar frequencies. But to create a negative index in order to manipulate gravity, that's quite a different problem. And I think it's going to be an area of research that is going to take many years to sort out. And as I was pointing out during my talk, I would advocate for gravitics labs, perhaps at places like JPL or Applied Physics Lab, people that are used to building things. And I think that would be a really valuable thing to do. And so far, we just don't, we haven't really seen that development happen quite yet.
Okay. So does anyone else have questions for Gary? Let me see. Ron, you have looked like you might have a few. You're muted, sir. Ron, you're muted there.
Yeah, I think he's still on mute.
Okay. Yeah, he's still on mute.
I'll ask a question.
Well, what Ron is actually trying to.
Ron, have you unmuted? Just looking for the unmute. I think you have to hover over the bottom to
okay, I got it. Yeah, I think Jeremy mentioned electron-positron pairs. No?
Yeah. Why, Ron?
Yeah.
It was Gary Chase from the live chat, but yeah, I brought it up for him.
Oh, okay. Because here is something from UFO. One of the most interesting books is called UFO Quest, and UFO Quest. You're familiar with UFO Quest?
No, I haven't seen it.
Yeah, it was written by Alan Watts, but it's not the Alan Watts that wrote The Way of Zen. What I'm going to do is just our fax machine at the library is broken, and so I sent this out via iPad. But I want to see if this comes across. There's the creation of electron-positron pairs down here.
Okay.
It's a magnetite sandwich. The top of the UFO is single crystal copper. And this was investigated by the University of Manchester back in the 50s.
Really?
And oddly enough, the University of Manchester, I'm linked in with somebody at the University of Manchester, I should know, but there are a few things that I've seen from maybe Rob Chambers will know, because are you familiar with Green Glow? The Green Glow people from BAE?
Yeah, I think they're here. Fran, if I can get off mute, and then Rob Chambers is here.
Yeah, because this was taken, this is all British. It's SILPHO, SILPHO more. And hopefully this will come in. And what they had at the top was a gamma gun that circulated. It went through a magnetite sandwich with a dielectric, a polymer dielectric of styrene that was of such density. I think it's easy to find styrene if we all burned, not that I burned many plastic models, but it's burn and sniff. When you burn styrene, it has the odor that's characteristic. And so I guess they did a burn and sniff, and they did a density test. And they said back in the 50s, they knew of no styrene of such density. And so one thing I get involved with is benzene ring materials. And when you subject them to electric fields, you change the electrorheological properties. They shrink together. They screw up my electrodes because they go away from the electrodes into the densest field. And so you think you have a complete electret, but what happens is you have a lot of vacuous space because of the contraction. But this was done with a magnetite sandwich. It's called SILPHO more, and there's 4 pages. Amazon has it for like $8. A few people I know bought it, but in terms of just being, some of the names in here are just incredible. The British Non-Ferrous Metal Materials Association, they're the ones who's ascertained that it was a single crystal copper. And it was a dual ply laminate. Also, Department of Metallurgy at the University of Manchester, the Cavendish Laboratory at Cambridge, and the University of Manchester came to the same agreement. And it's all within here. I do have a bad copy I can email out, but the main thing is it was copper as a superconductor two laminates, a magnetite sandwich, then a bottom layer of single crystal copper. So if anybody wants it, but with Jeremy, he was concerned with the electron pair creations, and it was done through this gamma gun at the top that rotated. So I'm out. Nice meeting everybody.
Good to see you, Ron.
Thank you again, Ron. So Wayne actually had a question. Wayne, let me unmute you there.
Yeah, hi. Yeah, so I wasn't able to listen to the whole presentation without interruption, so I might have missed a few things. I was just wondering about the forward coil you were talking about. I've seen that picture before on the internet, and it was intriguing. And I was just wondering if you could comment on some of the practical design approaches that we might take in making something like that, or what?
I can certainly address the challenges. And the first challenge is that G over C to the fourth term drives the number of turns in the forward coil extremely high. So you want a really high N. If you can get 1 billion turns, great. So that is going to be a design constraint. But with high permittivity or permeability core in the middle of it, that could shrink the number of turns needed quite substantially. Second thing is, if you're going to use superconductors, which I have proposed, winding the segments and then connecting the segments together also almost has to be, because the number of windings almost has to be robotic. So you need a machine to do the windings. Now, there are machines designed to do motor windings. That's how we get very inexpensive electric motors.
Yeah.
We would need to use and adapt some of those machines that do motor windings to doing these nanowire windings, only at a much different scale. So the scale of the nanowires is much smaller. The packaging of the nanowires and the connecting of the nanowires is problematic because you might be able to get current into a nanowire, but how do you connect it to other nanowires? That's been worked out for fiber optics. It's not been worked out for nanowires.
Okay.
One of the approaches to nanowires that William Reichen suggested to me was embed it in fiber optics, and then you can use fiber optic connectors to center the device. You still have the problem, even when you're bringing those two fiber optic pieces together with the superconductor itself. How do you make sure they punch together tight enough that you maintain superconductivity between two carbon nanowires? One of the reasons it's a superconductor is it's a crystalline structure. These nano wires are essentially aligned nanorods. So getting those nanorods to couple to other nanorods in a favorable way. The thing that works for you is they are slightly magnetic. You don't think of carbon as a magnetic material, but carbon nanowires made out of carbon nanorods are highly magnetic because of the alignment of the domains. So that might actually help you a little bit on getting these things connected when you try to start connecting these different segments together. So
that sounds like some advanced material engineering.
Yeah, you're gonna need some serious material engineers on this. As my co-authors, Marcel Grossman, were both material engineers. I was the only physicist, system engineer. The other two co-authors were material engineers.
So my interpretation of that, when I saw the diagram, my interpretation was that what was going through those coils was not electric current, but mass flow. So maybe a fluid or something that was
right. And my point is you're treating the electrons as mass flow. It's the mass of the electrons that are important, not the charge.
Right.
For electromagnetic effects and SMS devices, you want that charge circulating, the charged electron. For a gravitomagnetic coil, you want the mass of the electron. So here's another way to increase it would be push the electrons until they're relativistic. And so if you, and I have a table in my Marcel Grossman talk that shows the impact of different betas and gammas of different relativistic speeds of the electron. And the electron, with respect to the rest frame, which is where we want the gravitational effect to happen, if you push those electrons into a relativistic mode, they weigh more in the rest frame. And as soon as their mass goes up, you get more effect. Now, the problem with that becomes energy leakage, such as shrink-off radiation, as you get with any particle accelerator. So what you wind up having on your hands is a donut-shaped particle accelerator now. And so all of a sudden, with shrink-off radiation, you have all of the problems attendant with particle accelerators. So
is that related to the synchrotron radiation with the electrons accelerating?
Electrons accelerating through a medium, in this case a nanorod medium, are going to emit shrink-off radiation. So you're going to see that as an energy drain, as well as you might start ionizing air. This might start glowing blue.
Yeah.
Okay.
There's been a lot of talk about rotating Mercury in some of these discussions. Mercury being very dense.
Yeah.
But there's other dense
vapor. Yeah,
other dense liquid metal.
Mercury vapor. Another idea that's been tossed around that I actually disclosed to United Technologies was using liquid helium. It's a superfluid. Because superfluid, it has very low to no friction, as long as it's maintaining a temperature where it maintains its superfluidity. You can also ionize it with ionizing radiation to the point where you can use electromagnetic fields to accelerate the superfluid and manipulate the superfluid using pinch fields. I can't remember the name of the pumping. It's a kind of pumping where the diastolic pumps.
Peristaltic
pumps. So you can use a peristaltic pinch field to push the liquid helium through these tubes and accelerate it to extremely high rates. Ionized helium nuclei have a much greater mass than electrons, thus a bigger effect. The problem you wind up with there is it's going to be radiating because you're ionizing, so it's somewhat radioactive. So you have to have it in a chamber just for radiation, but it's a very weak radiation, but it will be somewhat radioactive, the test setup, simply because it has to be to ionize the liquid helium. So that's going to be a constraint.
Also a constraint is
Liquid Technologies took a pass on that patent. So I said, do you mind releasing your interest in it? And they're like, no, we're just gonna keep it for now. So they chose to not patent it and not release it. So less for anybody who discloses patents to companies.
One more little question. With the fluid, whatever this fluid or these particles be, would they have to be in like it would be a constant current or a pulsed type of current?
Well, the nice thing about a toroid is it might look like a constant flow, but the direction is always changing. So the energy tensor is changing. So the stress energy has a derivative even in a constant flow.
Okay.
You only need the change in flow if you're trying to do AC, if you're trying to do gravity waves, then you need a changing flow. But just to do scalar gravity, you can do it with the constant flow.
Okay, so let me go to, actually, before Mark jumps in, let me jump to Franklin, who has been patiently waiting with the question for a while. Sir?
Hey, Gary. Yeah, I've never really heard of this high frequency gravity waves, and I wasn't really sure why anyone would be interested in them. But just to try to clarify where you're at with your research, so it looks like you're proposing that these things can be detected, but you haven't actually built anything that has done a detection. Is that where you're at?
That's right. Yeah, that's right. I'm not building any of these. I think it's a good idea.
Now, what did you say was the actual connection you think between? There's something about the high frequency gives you some other power of something which makes something more detectable or something?
Yeah, in terms of generate, if you wanted to generate something in a lab and see a measurable effect, it's easier to generate high frequency gravitational waves than it is lower frequency gravitational waves. That's for the generation side.
What about during the detection? So I don't understand. It would seem that you have to understand what gravity is in order to build a detector of any kind of gravity wave.
Yeah.
What was the connection you're trying to make there?
Yeah, for detection, the interesting thing about higher frequency gravity waves is you can measure them cosmologically too, or you can use it in a lab to measure, did your generator work? So I would like to have a generator and a detector that work together so I can use it in a lab to measure the response of materials. Then you have a gravitics lab, right?
Well, it still doesn't tell me that what you've detected is, gravity per se. You must be theorizing there is a connection between the high frequency gravity wave, which I could create by, I don't know, spinning an iron rod around, I suppose. That would generate a higher frequency gravity wave. I suppose any kind of, electrical means of doing it. But that's kind of the way I'm thinking about it. You just take a ball of concrete and you spin it around as fast as you can. That should theoretically create a gravity wave. But from a theoretical standpoint, if you're talking about something electrical that's going to try and detect something like that, I still don't understand what is your connection, electrically.
Yeah,
because you did mention this connection between electricity and gravity, and we all want to find that. And it's like, but you'd have to have already made that leap, right?
The connection is the gravity wave itself. You don't want it to electrically be connected. The detector should be detecting the gravity wave.
Now, Gary, do you want a moment, Gary, or because I
could use a glass of water.
Yes, let me go for it, sir.
Okay.
Sorry
Well,
about that.
Gary runs off. I have a question for Franklin, maybe to clarify. What Gary was saying is that if you take a wave, like a photon emission or a very high frequency electromagnetic potential, and you squeeze it by external fields so that it takes up a smaller volume of space, the energy in that volume of space is higher because you've effectively compressed it. So as a result of changing the physical geometry in which the energy takes place, you produce a change in the fundamental space-time metric that's there. You change the space-time curl vector because you're conducting that field through some volume through a medium of space. And
you're still talking about actually physically compressing something, just like at LEGO, they're compressing the arms of like 2.3 meter, mile.
Plasma. You have a plasma that's traveling in one direction, and you squeeze that plasma down to a very small area, and it has, it's an ionized plasma, so its electric field is now in a smaller area, and it has a motion to it. So it's not just a uniform plasma, but it actually has a characteristic where it has areas of high concentration, low concentration in its energy. If you continuously compress and expand this plasma, it's going to have an effect on the medium that's carrying its electromagnetic functions, and that would be the space around it. So that's where you're going to get your emissions from, is from compressing the plasma and consequently increasing the volume of energy in a given space. Am I understanding that correctly, Gary? Because now you're back.
Yeah, so, right, you are. And actually, the important part about the third International High Frequency Gravity Wave Conference was I had a conversation with Andrew Beckwith on the Tokamak approach. And he did the math and felt the only way it would work would be if you had a burning plasma. Because if you're resonating the plasma in a quadrupole way, just the plasma oscillation didn't have enough mass to trigger the level of gravitational response that we needed to see. It needed to be a burning plasma. So ideally, if you had burning nodes, if the plasma is bouncing back and forth in quadrature, and when it hits together, it burns, right? It creates fusion. And when it bangs back, it creates fusion. If you have those 4 burning nodes, then that's enough mass energy change to be able to break the threshold of detection.
Yeah, I would imagine that is the big deal in detection, because gravity is so small.
That's because the coupling is so small. And the other way to improve that, which Sorfati is pointing out, is can you change that coupling constant, that G over C to the 4th coupling constant, using a material that helps exaggerate or concentrate those gravitational lines of flux. Just as we use an iron core in a coil, can we use high permeability materials to strengthen that gravitational coupling? And the answer he predicted through his S matrix, his zero rank tensor, looks like yes. Even in isotropic material with high permittivity or permeability, the answer seems to be yes. It seems to be more pronounced with permittivity. It goes to the fourth power of permittivity. It only goes to the squared power with permeability.
Well, then there wouldn't still seem to be a very good connection between electromagnetic, say, and gravity. I mean, actually, another reason why I tuned in onto this talk was that you said high frequency gravity. Now, basically, my own hypothesis is that gravity itself is actually a high frequency wave. Have you ever heard of that hypothesis? And,
that very well may be. I mean, one of the Mach's principles is that inertia is springing from the superposition of all these gravitational effects, and that's what's causing inertial drag. So under that scenario, you could reduce inertial drag by creating a frequency cutoff if you can somehow shield certain higher frequency gravitational waves, you can shield yourself from inertia. So there, you might be onto something. I mean, I don't know the theory behind all that.
Well, it reminds me a little bit about Bob Lazare's theory, where he said there's this A gravity and there's that B gravity. Now, to me, that sounds an awful lot like the symmetry we get in charges, where there's a positive charge and there's a negative charge, right? Yeah. So essentially, there may in fact be a negative gravity.
Right, and Einstein's field theories don't really take that into account. It just takes it as a given that there's one gravitational coupling constant. There may be more than one flavor of gravity. And in fact, Heim theory says that there is. I have published on ResearchGate, on my ResearchGate, a review I did of Heim theory a couple of years ago in which he predicted 3 different flavors of gravity. So you may want to take a look at Heim theory too. There were a number of mathematical errors that were found in 2011 or so. So people kind of dropped looking at Heim theory, and it's also very convoluted. But he was a German physicist that was trying to work on a unified field theory. And in order to make it all fit together, he had to have 3 different types of gravity.
I would think that, according to Bob Lazar, we'd expect to find 2 kinds of gravity, and he seemed to imply that the alien technology was such that you could actually create a gravity gun. I mean, I've kind of seen these on the cartoons where literally they have a gun that shoots a beam of gravity, and you can do things with it.
Yeah, I did present in the 3rd gravitational wave conference heterodyning 2 high frequency gravitational waves to get 1 low frequency one, and to see if we took 2 high frequency ones, heterodyned them together with a small frequency difference, could we create a signal strong enough for LIGO to measure? I think kind of the jury's out. It depends upon what kind of generators we're using. With burning plasma generators, it may be possible, but we would need at least very strong burning plasma Tokamak generators to be able to pull it off. But that is also another way to create like a tractor beam or a gravity weapon, as it were, where if you take a very small frequency difference between 2 highly tuned high frequency gravity waves, and you're getting that small difference between, or superposition between the 2 of them, is there a way you can create a scalar effect there? And there may very well be.
Yes, there is. Okay, sorry. Yeah, Mark had a question as well. So.
Oh yeah, I just wanted to comment on what Franklin was saying. First of all, my belief on Bob Lazar is that he saw real craft and he was fed a BS explanation as to how they operate. And one thing that was very telling about his presentations, especially the early ones, is that when he went into the base of the craft, he saw what he thought looked like microwave waveguides, and they told him they were gravity waveguides, and they're moving this gravity A wave and B wave and of an element 115 that turns into element 116, which is antimatter, which we all know is impossible. So I think the explanation that he was given is complete BS. It was meant to lead us in the wrong direction. But that insight that there was microwaves in the base of the craft, tuned tubes or tuned cavities in the base of the craft, really has something to do with how the craft operated, instead of being actual gravity waves. And that fits in more with the dynamic nuclear orientation aspect of how these craft can work with the Alciphon theory, which we'll get into later.
Okay. So I think we're just about there. Does anyone else have any more questions, or should we
Ron did, but he wasn't able to unmute.
Oh,
so you need to hover towards the bottom of the window, Ron, and look for the mute. Unmute.
You hear me now?
Yeah, I can hear you now.
Oh, good. Right. I'm very interested in your metamaterials.
All right.
Especially with the forward toroid. But
I think it would be a good combination. I think it'd be really interesting to look at the effects of that. And that's something that's driving me towards, why don't we get a gravitics lab that can start looking at
You need a gravitics lab.
I think so.
First of all, I mean, I would go back right to linearized gravity. What you first of all need to do is to be able to generate gravitomagnetism in your gravitomagnetic lab.
Once you have that, then you have a source of a signal that you can use to see the effects of other materials, but you need that link first, that generator and detector, before you have a lab.
Right. Let me just throw something in. You've heard of Faraday rotation?
Yes.
Right. I think that may be the way to do it.
Well, some of the sightings have said that they've observed Faraday rotation. So very interesting. I mean,
no, I don't mean. I mean the Faraday rotation with a changing. Well, normally it would be with a magnetic field. Does Faraday rotation work with gravitomagnetic field?
Yeah.
In which case we might be
able a detection. You're saying as a detection mechanism.
As a detection mechanism, which we haven't done yet.
No, I haven't looked at that actually. That's a good idea.
Yes, and I think we might find in a laboratory on Earth we can create gravitomagnetism and detect it, which nobody has realized. Well, we looked at the Earth rotating and its gravitomagnetic field, and the gravitomagnetic permeability of space is virtually zero. But inside materials, as you said,
materials, exactly.
Yeah.
If we do this inside materials, it will have a whole different effect.
Yes.
As that S matrix just pointed out, right? This is what Jack's been on about.
That's what we want, a metamaterial for gravitomagnetism, not for magnetism.
Right. It will be a different design.
Yeah. It'll be a different design. Yeah. Well, the US has got the money. UK's got no money.
We're not spending it in the right places.
Okay. Right.
Thank you, Tim. To prop up the stock market.
Well, Gary, we would personally like to be your go-to gravity lab.
Fabulous. I'm glad someone's
do that for you.
Actually, we've had early on, we had an intern, Adam Keegan, who actually worked on LIGO. He was in charge. Yeah, he was in charge of the interferometer setup.
Yeah.
The one thing that people don't realize about LIGO is that it's not just one observatory. There's several observatories around the world, and the equipment is so sensitive. They're measuring car crashes 10 miles away, or trucks driving over a bridge or something like that. They're extremely
multiple. Yeah, you need one in Hanford. You need one in Livingston. Yeah.
Yeah, you need one all over the world. One in Germany. That's why his professor actually had to split the Nobel Prize over it, because the only way they could really say that this came from out of the planet was because they got the same impulse in Germany and here in America at the same time. So
Virgo.
Yeah, these gravity wave detectors that they're dealing with, the laser interferometer system, they're very, very sensitive to noise, and it's not really applicable to a lab. But what you're talking about is something that's literally tabletop.
Yeah, exactly. Yeah.
And as long as we can figure out how to get that 9 Tesla field without blowing everything up, I think this is something we can do here in the lab. We have enough wire, we have enough current. Hybrid battery systems can definitely provide that much power.
Up to 300 kilowatts.
Yeah. I mean, I can combine it. I have several tons of nickel metal hydride batteries in storage. We can charge them all up, and any amount of current you want is available here at the Falcon Space Lab.
That's great.
And if you want to fly down here to help us out with it, all expenses paid. It's already taken care of.
I would love to have a look sometime.
Okay, well, I think we're just about done. So again, let me unmute everybody and we will give Gary an enormous applause. Sir, thank you so much. Thank you so much. So let me invite everyone to unmute. And again, enormous applause for Gary. Okay.
Great job, woo!
Okay, so next we are going to go, and he has been with us, Todd Desiato, and Todd is going to be talking about quantum gravity. Let me see. And Todd, are you with us?
I am.
There we go. There we go. Okay. Oh, sorry, I have a little bit of. Okay. Perfect. So Todd, what can I help you with, sir? Are you ready to get started?
Yeah. Can you see my screen?
Oh, perfect. Perfect. Okay. I will mute myself and I will just disappear into the background here.
Yeah, for some reason, when my screen takes over, I lose the view of everybody else.
Yeah, mine does the same thing. It maximizes. It's kind of a Zoom bug. Okay. Well, again, Todd, thank you very much. Quantum gravity from atomic resonance effects, and I will hand it over to you, sir.
All right. Just know I can't see the chat or if anybody is raising their hand because it disappears when I share my screen. Anyway, this model of quantum gravity started over 20 years ago, 23 years ago. My buddy Rick Storty and I were working on gravity in terms of a refractive index, variable permeability and permittivity. And we used this refractive index model, and about the same time, Hal Puthoff published a paper about the polarizable vacuum model. And we kind of worked in parallel, not really together, but in parallel, came up with very similar models. Over the years, though, I continued where Hal stopped, and I have brought this to a quantum level where, using some of Hal Puthoff's more recent papers on quantum ground states and a lot of information from Peter Milonni about the 0-point field and the quantum vacuum. Now, part of this comes about from having a similarity in dimensional analysis, and from Einstein's equivalence principle, accelerated reference frame is equivalent to a gravitational field, at least over a small enough area, volume. So from that, we use this idea of similarity to investigate various models of gravity that, and in looking for a way of engineering using, modern technology, not something that doesn't exist yet, in ways of affecting gravity. And what I have here is pretty much a culmination of that research over the past 20 some years. So it starts out with the notion of quantized magnetic flux. Here, phi naught is the quantum of magnetic flux, which comes from studying of superconductors. And when they say you have a pinned flux in the superconductor, this is what they're talking about. These are the quantum flux lines that get pinned in the superconductor. And it's basically Planck's constant over the unit of charge. Resistance, quantum of electrical resistance. I bet you didn't know resistance was quantized, but H bar over E squared is the quantum of an ohm, or ohms. I shouldn't say it's not 1 ohm, but it has resistance, electrical resistance. And scalar magnetic flux, as Richard talked about last week, is a real field that exists, and it was shown to exist by the Aharonov-Bohm effect, and we know this is true. And so we use this phase shift to describe gravity. And if you think about it, when you have the action, and I don't have this on the slide anywhere, but when you have the action, and in the Aharonov-Bohm effect, the electron adds a phase shift. Well, if you apply a metric other than a flat Minkowski metric to that equation, all it does is add more phase shift. It doesn't do anything else. The metric just changes the phase shift of the wave function, just like the Aharonov-Bohm effect. There's that similarity I was referring to. So scalar magnetic flux plays a very important role here. And you can see that in a electromagnetic gauge potential, looking at the magnetic gauge potential in particular, the initial gauge potential is modified by the gradient in the scalar flux. So the gradient in the scalar flux is non-rotational. So when you take the curl of the gauge potential, it plays no role in generating a magnetic field. And so, but that flux, what I'm proposing here, and this is the one of the primary assumptions, is that scalar flux is real and that it does not affect E and B, our electromagnetic fields, but it does affect the gauge potentials, or the electromagnetic potentials, as I like to say. So here's a picture, courtesy of MIT, showing magnetic flux passing through a superconductor, and you can see at different flux densities around the graph, the flux lines get tighter and tighter. So for an electron, we're going to think of scalar magnetic flux as the photons in the 0-point field, or at least part of them. Doesn't have to be all of them, but it's contributed from the 0-point field. And if you want to think of it in terms of Mach's principle, this is the summation of all the other magnetic fields in the universe, all conspiring to affect this electron we're talking about here. So assuming that the rest energy of a fermion, electron, a quark, can be written as mc squared is equal to Planck's constant times a frequency, where that frequency is the Compton frequency, then we assume that the frequency is a Larmor precession. This is an assumption, but we're going to look at this assumption, and then we're going to say that this point-like electron, which is how an electron is described in QED and from scattering experiments, it's extremely small. But when it's interacting with the vacuum or an atom, it looks like a cloud shown here. And essentially that point is being bombarded in every direction by the 0-point field and its own re-emission or radiation reaction. So that process of emitting and absorbing photons from the 0-point field essentially inflates this point-like particle to a cloud. And according to Milonni and experiments, the cloud is on the order of the Compton wavelength. So the size of the cloud is the Compton wavelength, and that Compton wavelength comes about by a point-like particle being bombarded by photons from every direction to inflate this cloud to this size. And, using the equation for the Larmor precession and the charge to mass ratio or gyromagnetic ratio, we get a Tesla field at the scale of an electron of 4.4 billion Tesla. enormous amount. But you can do the calculation, and if you take the area of a Compton wavelength squared, we're only talking about 25 flux lines at any given time passing through that area. In the 0-point field, the statistical average of the magnetic flux is 0. So where it's not 4.5 billion Tesla, it's 0. But the instantaneous bombardment of that point-like particle sees flux lines that are on the order of this 4.4 billion Tesla. Now, electromagnetic flux, we said, was Planck's constant divided by the electric charge. Well, what does that mean? That here, it means that this is angular momentum per coulomb. So angular momentum per unit of charge. That's what magnetic flux is in terms of, its physical effects. It's the angular momentum of the charges. And so what is gravitomagnetic flux? Well, it turns out it has units, and remember I mentioned dimensional analysis, it has units of frequency or hertz, but really hertz breaks down into the angular momentum per unit of mass. So again, to convert from magnetic flux to gravitomagnetic flux, all you need is the gyromagnetic ratio, or the charge to mass ratio of the particle. And it's critical to understand that. This is why something like Alzaphon experiment and NMR and Paul's Searle disk can affect gravity and the weight of objects, because this gravitomagnetic flux is intimately associated with the spin of the electrons and the protons and the quarks and the matter that is being affected. So in the paper that's being published in the proceedings from the Estes Park workshop from September, it's proposed that gravitational fields may be interpreted as a reduction in the relative available power or driving power in watts of the electromagnetic 0-point field as it interacts with matter. Gravitational time dilation and length contraction may then be interpreted as a loss of power from this interaction between matter and the 0-point field. So in a sense, that electron cloud that got inflated in a gravitational field contracts. It loses power, it loses diameter, the Compton wavelength contracts, we have gravitational length contraction. The relative radiating damping factor affects the relative ground state energy of the quantum mechanical harmonic oscillators that make up matter, basically, such that the mean square fluctuations of matter reproduce the behavior attributed to and resulting from the space-time metric of general relativity. And so, because matter behaves this way, we get an observation of space-time's curvature. From this principle, the phenomenon observed by a distant observer that are due to gravity, such as time dilation, length contraction, redshift, gravitational lensing, can all be reproduced from a variable relative damping factor acting on the harmonic oscillators that make up matter. Utilizing magnetic resonance imaging apparatus, or nuclear magnetic resonance, or electron magnetic resonance, or electron spin resonance, to stimulate Larmor radiation, experiments may be conducted which can demonstrate gravity and anti-gravity accelerations. In other words, weight gain, weight loss, propulsion, things like that these experiments can be done, and basic physics will tell you that it should work. And let's continue. So going back 20 some years, we have the polarizable vacuum model, which essentially you take simple two-dimensional metric and calculate a refractive index for the speed of light. here we calculate the refractive index for the speed of light. We define a relative index of refraction, which for the surface of the Earth and in a spherical potential, same as a black hole, we get the Schwarzschild solution. Now, this is slightly different than what Hal Puthoff gets, but we've gone over it several times, and it's a matter of taste how you want to solve it. But because it produces the Schwarzschild solution or Hal's solution, which is an exponential decay, then all the experiments such as the perihelion of Mercury, gravitational redshift, time dilation, gravitational lensing, all those things, all those experiments don't change. They're predicted just with this polarizable vacuum model, just as they were with general relativity. And so those experiments support this model just as they do support general relativity. But here's where my latest research comes in, and that is that instead of the refractive index, which really doesn't help us to engineer anything in a vacuum, we now look at it as a relative damping factor. And so the radiative damping interpretation of general relativity is we define a relative damping factor in terms of power loss. As I said, gravity is power loss. So power, subtracting a small loss amount, which is this zeta squared, and zeta squared is what Jack would call the susceptibility. And again, Jack just took the permeability and permittivity that Hal and I were talking about for 20 years and turned them into tensors, fourth rank tensors or zero rank tensors, however you want to put it, once you multiply them together. But essentially, he took that idea and expanded it into tensor math. Not sure that helps engineering any, but it does give him something to do. Anyway, what it turns out in this model, the speed of light and power are covariant. And what I mean by that is if you affect the refractive index or you affect the radiative damping factor, it'll affect the power in the same exact way. It'll affect the coordinate speed of light. So that refractive index changes, the coordinate speed of light changes, but it's exactly the same. Power and the speed of light vary the same way with a change in damping or a change in the refractive index. So if you're looking at it from far away and you see an object falling into a black hole and you see its clock starts running slower and the object is contracting, its power is getting lower, the speed of light is getting slower. So from far away, it looks as though it's slowing down because it's losing power. And so that's the whole premise here. And from that, using Hal Puthoff's paper on particles, we find that the fluctuation in the position of a particle, this is the solution for a quantum mechanical harmonic oscillator, loses by this damping factor as which would be like 1 over k, but the velocity squared loses power like 1 over k squared, or this factor squared, and acceleration is to the cube to the third power, but mass is 1 over the third power. So these are the variations with damping, how damping affects the fluctuation in position, the fluctuation in velocity, fluctuations in acceleration, and fluctuations in mass. And these are the same mass fluctuations that like Jim Woodward talks about. And this is why he can make it vary. But power comes about by the quantum fluctuations in power come about by multiplying these three expectation values together, which gives you the square of the above equation from up here. And that's how, power and the speed of light and velocity and acceleration and mass are all affected by radiative damping due to Larmor precession. Now, as power loss, we have this radiated power, and This is Larmor's equation for Larmor radiation power. This power is what the power that is absorbed from the 0-point field. And this came from Hal Puthoff. It also is in Miloni's quantum vacuum book, excuse me. And so these two are related in that they balance. It's a symmetry. It's a symmetry of nature. Conservation of energy, power in equals power out. So to maintain that probability cloud at the same size requires that we have conservation of energy, and the amount of power absorbed by that cloud is equal to the amount of power it radiates. Now, here's the catch. When this symmetry is broken, it accelerates. And we know from the equivalence principle that accelerated reference frame is equivalent to a gravitational reference frame. So when this equilibrium condition of power is broken, we get gravitational acceleration. So this acceleration over here changes and exceeds this, so we get motion in one direction or another. And in the case of free fall, we fall toward the ground. The damping factor near the surface of the Earth, and here I've used the mass of the Earth and the radius of the Earth in this number, we get 2.638 times 10 to the minus 5. So that's your damping ratio. The factor G, which we know is 9.8 meters per second squared here at the surface of the Earth, is essentially, G squared is essentially the power per second, power loss per second per kilogram. And so for an electron in free fall is losing, relative 1 point in the free fall geodesic to another, it's losing power at a rate of 8.76 times 10 to the minus 29 watts per second. And a proton would be losing power at a rate of 1.609 times 10 to the minus 25 watts per second. And essentially, in terms of just kilograms, G squared is, a kilogram is losing about 100 watts per second per kilogram, which that's great news because that's not a huge number. It's doable to replace this energy and negate gravity, but it's 100 watts per second per kilogram. So you have to keep it up for that can build up very quickly. So how do we use this to derive gravity in an experimental way that we can test it? So we have the energy is offset by this factor, and this is from the polarizable vacuum model, and it's just we're losing energy. So we have this factor here, and we have our gravitational potential energy, and so there has to be a gradient in the potential in order to get G as 9.82 meters per second squared. And so if the gyromagnetic ratio or charge to mass ratio of an electron is held constant, then that energy is essentially Planck's constant times the Larmor equation for the frequency. And so we can generate a force on the subatomic particles, quarks, electrons, protons, by having a variable or a gradient in the magnetic scalar flux. So the magnetic scalar flux density has a gradient, not a direction. The gradient has a direction. In this case, it's radial, but the scalar flux itself does not have a direction. It's a scalar. So we have a gradient in the scalar flux, which generates a force on the quantum particles that expands and contracts the volume. Like if it moves up, the volume of the probability cloud expands. If it's falling down, it contracts, which is what the Ricci scalar does in Einstein's equation. So it controls the volume of matter. And so with the Ricci scalar, this just derived why that is. Okay, so acceleration is, in terms of gravity, is damping. So when you have the scalar magnetic flux, we have to imagine that the scalar magnetic flux density is higher up above than it is down below. And so there's a gradient there that increases the value of the scalar magnetic flux as you go up. This relates to the frequency that, change that we call time dilation, is that if the particle is falling down, its Larmor precession frequency is decreasing. And if it's going up, the Larmor precession frequency is increasing. So for every subatomic particle, this is happening, and this is why you have to do work to lift things. This is what is, you're actually putting energy into the spin of those particles as you attempt to lift them. And essentially that energy that causes free fall is coming from the matter itself. And it's always said in general relativity that it doesn't conserve energy. Well, this is why this part of it isn't being explained. It's being, wished away basically by a geometrical interpretation that wants to, keep space-time curved. Here, I don't need space-time curvature. That's all gone. It's what you measure with a ruler and a clock that expands and contracts or changes rate according to the background scalar magnetic flux. And so in that sense, general relativity and the geometric interpretation of space-time is just that. It's an interpretation. And this is a different interpretation. You don't want to mix the two. You don't want to say, you don't want to do this quantum mechanics in a curved space-time background that's redundant. So you want to derive the curved space-time background from the quantum mechanics, and that's what I'm attempting to do here. So, this slide basically comes down to saying that we have the refractive index is the ratio of magnetic flux at one point relative to wherever you started, the initial flux value. And so that's what will determine whether your refractive index is increasing or decreasing, or if you're going uphill or downhill. This is a really good slide. It just shows that to control magnetic resonance, the random spins, you apply a magnetic field and all the particles line up, but regardless of all the particles lining up in a magnetic field to do resonant experiments, the lowest energy state is still when they're random. All right. So I did a little calculation here. It's a back of the envelope calculation of what is the gradient in the magnetic flux density, the scalar magnetic flux density at the surface of the Earth for an electron that an electron would see. And essentially, massive electron and the gyromagnetic ratio, and we get the Compton frequency. And so this would require a gradient, delta B over delta Z, that is 4.8 times 10 to the minus 7 Tesla per meter. That's really not very much. And it would cause a time dilation shift of approximately 13.5 kilohertz per meter, or essentially 13.5 hertz per millimeter, which again is a very small shift in frequency in order to generate 1 G of acceleration for an electron. Do that for every electron. Then we have, for a proton, same calculation using the magnetic gyromagnetic ratio for a proton and the mass of a proton. We get a frequency of about 24.8 kilohertz per millimeter, or megahertz per meter. So this, again, it's not a huge frequency shift. It's not a high energy phenomenon. It's just a shift in frequency, kind of like the Zeeman effect in matter, but you have to do it in a way where it's you're not splitting frequencies into higher and lower. It's going to be higher where the magnetic flux density is higher, and it's going to be lower where the magnetic flux density is lower. So I want to point out, though, that even if this is not how gravity is, it is still a useful way to engineer gravity or anti-gravity or propulsion or weight loss. It's a way to mimic gravity, to apply it in a way that is friendly for engineering. And as an engineer, that's what I prefer. So also I did the neutron is also, it's about the same as the proton. And, so not a long talk, but I'm just going to read through the conclusions because this may give you some ideas about entanglement in quantum mechanics. When the spin of a direct particles are fermions, they're electrons, quarks, neutrons, protons. They're entangled. They share a common bundle of magnetic flux because they share a common state and a common angular momentum. So the magnetic flux is the angular momentum per unit of charge. So if they share a common angular momentum state, then they also share a common bundle of magnetic flux. In a vacuum that's far from other material objects, this bundle is highly coherent, meaning the oscillations of both particles are phase locked, the magnitude of which is represented here as the magnitude of B naught, my scalar magnetic flux density, and where the statistical average in a vacuum is still 0. In the presence of other objects such as planets, etc., black hole, the entanglement loss loses coherence and the value of B naught is reduced. So entanglement is related to gravity, but it's gravity that is destroying the entanglement. It's causing the magnetic flux density that binds that entanglement together to be lost. And so as that happens, particles fall, they lose energy, just as they lose power. So artificial gravity, using our understanding of nuclear magnetic resonance and an electron paramagnetic resonance or spin resonance, we can stimulate identical effects in matter. And that's what I'm trying to do here in my home lab myself. What is required is a suitable bandwidth to assure maximum coupling between the RF field and the objects, and suitably sized scalar magnetic field gradient to guide the processing particles in the desired direction. Now, we all know that frequency is related to energy. And if I have a gradient in the frequency, I have a gradient in the energy, which will exert a force. And so I am very confident that with this method, I can show weight loss or weight gain and motion of objects using that force. What I would like to also show is that these effects affect time dilation and length contraction, which I have not thought of an experiment that can do that yet. Anti-gravity is more than just directing the field gradient away from the Earth. It's more than just turning it upside down. In a real anti-gravity field, the power that drives the point-like charge of an electron to inflate to a probability cloud the size of a Compton wavelength needs to be amplified to overinflate the particle. So in a sense, that cloud has to get bigger. This is what happens when we lift objects up. They're going to a lower damping. The power symmetry is different, and the particle inflates, and as it falls down, it contracts. So to have anti-gravity, you literally have to inflate it. And if any of you are Star Trek fans, you may remember on Star Trek Voyager, they had a really good graphic when the ship goes to warp. It stretched into the distance and then flash a light and it was gone. That's the effect of a warp drive. It's the ship expands, everything about it, anti-gravity, you're raising the speed of light, you're increasing the power, it inflates the ship, the whole ship stretches into the distance and is gone. That's the way warp drive is going to work. The distance between point A and point B in space-time is shorter because the ship is longer. Anyway, so again, instead of length contraction, we have length expansion. Instead of time dilation, we have time accelerating and frequencies increasing. Matter becomes less dense. Now, this is a key point because warp drive requires exotic matter. And exotic matter, according to general relativity, it's not antimatter, It's not negative energy. People get that confused all the time. It's negative energy density, a density of energy in matter that is less than what it normally would be. So this negative energy density comes about by when you inflate that cloud of the particle and all the particles on the ship, that volume is increasing faster than the amount of energy you're putting in. So the density goes down as the ship inflates. And so that's the nature of exotic matter in warp drive. And the whole notion of, oh, I'm contracting space in front of the ship and expanding space behind the ship is a backwards interpretation caused by a geometric interpretation of space-time, as opposed to a physical interpretation of how matter is affected by gravity. And I hope I made that clear. That's pretty much the end of the talk.
Wonderful. Todd, thank you so much. So let me do this. Let me unmute everybody and let's give you an enormous applause. Thank you.
Hey, thank you.
Thank you again, Todd. So let's do questions and answers. And let me see. Mr. Murad again. Okay.
Hey, Todd, can you hear me?
Hey, Paul. Yeah.
Great conversation. Let me ask you one question. Your damping factors are usually values less than 1. What would ever happen if the damping factor was imaginary, an imaginary number?
If the damping factor were an imaginary number, I don't know how to do that. That would be essentially.
It's when your B factor gets bigger than your B0. Let's say.
Yeah, I don't have an answer for that. I don't know what would happen. I don't know that it's possible.
Okay. That's acceptable questions. Answer.
Yeah.
Okay, well, thank you, Paul. Let me see, and who else would like to go? Does anyone else have any questions for Todd? Oh, and there's Wayne. Okay.
If anyone in the chat room has questions, all caps for anyone in the live chat.
Hi, Todd. That was a great explanation. I was just wondering if you could comment on how the Earth would generate the gravity field, or how that interaction might,
yeah.
Yeah,
like I was saying, in a vacuum far from the Earth, right, far from any other matter, then we have an entanglement that is very coherent, and the coherence is a resonance, in that atomic state. And when you're at resonance, you've got your maximum inflation up to the point where the 0 point field is going to inflate that particle until it reaches the limit set by the damping factor. So the Earth is a conglomeration of uncountable number of particles that are all radiating electromagnetic fields, and all kinds of particles. So we're bathed in a particle soup right now, and the probability distributions of all those atoms and particles surround us. So their interference, they're a destructive interference that acts on that resonance that causes it to collapse, and as it's collapsing, it falls. It increases the resistance.
Okay, that's good. Thank you.
Yeah. I wanted to mention, Tim, about some of the experiments I'm trying here. Behind me in this picture is my little new lab bench I set up. And essentially, I am trying to make my own little nuclear magnetic resonance experiment here. And I've tried a few things, but I can't generate a sufficiently uniform magnetic field and with a large enough sample. So I have ordered some more toys to play with, some very large inductor coils, air core inductors, some pair of Helmholtz coils, and some more equipment that I'll be able to use to generate an NMR signal. Once I have this NMR signal in a sample tube, I should be able to generate with a gradient coil, a gradient field where I can physically show on an oscilloscope that the resonance frequency changes in one direction up and the other direction down. And then I can weigh a sample in this field and show that the weight increases or the weight decreases due to this force that I was talking about.
Okay. Paul.
In 2001 and 2002, I got very heavily involved with a Russian scientist named Dyatlov, who felt that Shipov's physical vacuum, which was homogeneous, was not good enough. So he came up with an inhomogeneous physical vacuum. And what he had was distinct boundary, more or less, whenever you had an anomaly. And when you were inside that enclosure, you had a different gravitic, electric, and magnetic field than outside. So you had this boundary. Now, he came up with a index of refraction, like you show. And from what I could tell, Puthoff went further by deriving a partial differential equation.
Yep.
Now, you mentioned that you went further than he did. I was curious if you looked at it in terms of coming up with a more advanced partial differential equation or more realistic solutions to that equation.
Well, to my knowledge, what Hal Puthoff came up with was a Lagrangian density for the field. And that's the only partial differential equation I'm aware of. And my understanding was that he got that from Dickey and from, I think it was a 1957 paper from Dickey about this type of scalar gravity model. And Hal came up with a Lagrangian density and modified it and got his own exponential solution. And then in around, I guess it was 2003 or 2004, a friend of mine who I used to know online, Joe Depp, wrote a couple of papers where he showed that there was an inconsistency in Hal's Lagrangian density that showed where it was an inconsistent, because if you're going to always say that the speed of light is c over k, then in the leading constant, c to the fourth should be over k to the fourth, and Hal had c to the fourth over k squared. And when Joe put in c to the fourth over k to the fourth and solved for the equations of motion, he got Schwarzschild's solution for the radial equation, not an exponential solution. And I showed that essentially that whole Lagrangian density breaks down into the Laplacian del squared times 1 over the refractive index. And you just do that and you'll get Schwarzschild's solution.
Well, that's interesting. What I'm kind of curious is, did he have a look at any sort of experimental validation of that approach?
He, in his first paper on it, the polarizable vacuum approach to general relativity, he goes through all of the tests of general relativity and shows that his approach fits the data. So he literally calculates out the perihelion of Mercury using his equation and his solution, and does this for time dilation, length contraction, and even later published a paper on the Levi-Civita effect. So yeah, he's done a lot of, he hasn't done the experiments, he's done the calculations that justify his solution fits the data from those experiments.
Well, I'm just kind of curious if you went using extension or using experimental evaluation somewhere that was outside of the realm. And the other thing is, I was just kind of curious what would happen if you had a singularity. Now, if you say his problem was different because of that, not getting the other recognition, I'm curious what would happen if you hit a singularity.
I'm not sure what you mean by hit a singularity.
Let's say you have a nuclear explosion. You could look at that as a singularity. Let's say you have a propulsive device and something great happens when you have a singularity there, then you want to maintain that singularity. So that's the whole thing I'm thinking about.
I don't know, because I in my model, and I'm not sure if I buy this or not, but since I'm talking about matter, not space-time curvature, what I get from that damping factor, the damping ratio, is that if the damping ratio goes to 1, all motion stops. It's frozen. So it's like at the event horizon of a black hole, there's nothing beyond that. It's stopped right there. It can't go any further because it's critically damped. Or I should say way over damped is what I should say. Yeah. It's damped to the point of no motion at all.
Okay, thank you.
Yeah.
Okay, thank you again. Jeremy, do you have any questions from the YouTube Live that have come in?
Yes, I do. I have a question here from Quantum Mac. How does one measure the increase in the diameter of the point cloud of an electron?
You can't, not yet, but you can measure the electron cloud on an atom. And this has been done recently. They showed an experiment. I saw it on one paper or another, one site or another. I saw it was a picture of the atom and with all the probability clouds there, but it didn't show any spacing. Now, going back 2015, 2014, Dr. Sonny White at NASA and Paul March did some modeling on COMSOL, and they modeled atoms in different vacuum environments and showed that if you had an anti-gravity field or a warp drive propulsion, that these atoms would in fact expand. And so their data from the simulation shows it's possible. But other than that, I don't know of any way to do that. It's easier to measure time dilation because you can measure frequencies very, very accurately using spectroscopes.
And then I had another question about what about using muons instead of the electrons, because they're very similar, but they have a little bit of a higher punch, of course.
Same thing. I mean, it would work. It applies to any fermion.
Right. Any more questions from the live chat? Please put them in all caps. And thank you very much for your time today.
Okay, yeah, and thank you again, Jeremy. And then let me see, Paul had another question. So
Todd, at one of the STAFE conferences, you presented a paper for a propulsor using 4 antennas.
Yeah.
It looked very promising. Whatever happened to that?
In terms of what I proposed as a design, I went through it and essentially found where it can't exceed the speed of light. And essentially what it comes out to be is a photon rocket, which is designed as a unidirectional antenna. So it's basically broadcasting electromagnetic waves in one direction and moving in the other direction, but can never exceed, the thrust of the photon rocket.
I'm sorry to hear about that because it sounded pretty good and it's pretty simple concept.
Now the equation I got there in that paper from 2003, I think it was, warp drive propulsion within Maxwell's equations. That paper, I derived a scalar potential field that was a solution to this electromagnetic version of Cubier's metric. And in that, it's very similar to what I'm talking about here. It's a charge to mass ratio where Q is the charge on the entire ship and M is the mass to be transported. And then you have a scalar field potential that causes transverse oscillations, which could be thought of as these Larmor Precessions that would then propel the craft forward. So I wasn't that far off,
You're not saying a pilot inside the spacecraft's got to bounce back and forth to get it going, right?
Yeah, well, we'll see. But the equation is there, and it amazes me that what I've got now takes me all the way back to there and says, oh, I had the same thing then. I had the charge to mass ratio multiplied by a scalar field, and I got propulsion from it. And here I'm just taking it to the quantum mechanic level instead of the electromagnetic Lagrangian density level.
We only learn from the past.
Okay. Moving forward, I like that. Anyway, I hope to have some experimental results soon. I do post my videos that I get on my YouTube channel, which is Warp Drive Tech. And Tim's welcome, and so is Mark welcome to post any of this on theirs as well.
Yeah, I would say send that over. Gary sent me his material earlier. Just send me any links that you want. I will add all of these in. Yeah. Well, so I think if we're all set, if we don't have any other questions, again, Todd, let me unmute everybody. We should probably figure out a better way to do this, but let me unmute everybody and give you an enormous applause. Thank you, sir.
A lot of fun. Thank you.
Thank you again.
Oh, man.
Okay, so let me put it on gallery view. And actually, let me go to Mark. I think, Mark, you had a lab update, right?
Working on it right now. We're working on it right now. Can you hear me?
We also had a question about the static. What do you call? He wants because Kazadin is asking to please elaborate more on the magnetic scalar potential.
We have more questions for Todd. Okay. Well,
or anyone in the audience who can talk more about and explain what magnetic scalar potential is a little bit better.
Yeah, and that's.
Could they mean gravitomagnetic scalar potential?
Todd, I think you're muted still, sir.
I said the magnetic scalar potential, it's as Richard talked about it last week. Essentially, you get a magnetic scalar field when instead of taking the curl of the magnetic vector potential, you're taking the divergence of the magnetic vector potential. And in the Lorentz gauge, they set that equal to 0. But in I think I got it backwards. The Coulomb gauge, they set that equal to 0. In the Lorentz gauge, you end up with the divergence is equal to the time rate of change in the electric potential. So the divergence of the magnetic potential is equal to the time rate of change in the electric potential. But that divergence of the magnetic vector potential is scalar magnetic flux, basically.
Wonderful. Thank you. Okay, well, Mark, are you guys ready now?
In 10 minutes. We need a couple more minutes.
Okay.
Can you hear me?
Oh.
Can you hear us?
Ron, you'll have to.
Can you hear me?
No, we can.
I can hear you now, Ron. I'm sorry.
I'm sorry. All I was going to say is I'm going to go now. It's coming up to 11 o'clock here.
Oh yes. Thank you for joining us. Thank you very much.
It's been very interesting. I may join you again if you're allowing me to join.
Yes, well, in fact, I would love to ask you to present sometime because you used to run the BAE Green Glow program, right? So
that's right.
I would love to. I mean, that program was legendary. Oh, okay. Well, Ron, let me let you go for now, sir.
Thank you very much.
I think we've. Oh, okay.
I know lots of people. Hello, yes, Gary Stevens. I remember, yes, and you and Ron Kitter, of course. Yep. Bye-bye.
Bye-bye.
Bye. Can you hear us? Yes, you can hear us. Okay. Jeremiah, can you try your mic? We're working with lapel mics.
Yeah. Can you hear me?
Yeah, we should mute one of those though. You're coming through on two, so I guess you need to determine which camera you want to speak on.
We're coming on just, we're trying to get on just the.
Your laptop and your lapel mic are both coming through?
No, that can't work. Can you hear this? I'm tapping it. Okay, they can hear that. Okay, so the lapel mics are working. So we're here at the lab in Hawthorne, New Jersey, and I have a mobile camera that I used to allow us to show us around the lab. And let me show you guys what it is we are doing over here. Jeremiah's working on some stuff on the board, but this is a lab space that we recently just set up. This is in addition to the Faraday cage and the control room we have out on the other side of the lab. There's a bit of construction going on over there. We're renovating the bathroom and some other stuff. I'm not going to join with audio on this one. And this is pretty much our lab setup. We have the gyroscopes. Right now we only have one gyroscope. This is for the gyroscope precession experiment. They're coming in from the United Kingdom, from Great Britain. It should be here sometime later next week. And we're also working on ALZAFON, which is the dynamic nuclear orientation experiment. We have two systems to run this experiment. Basically, it's a laminar magnetic field, similar to what Todd was talking about. You need to create a laminar homogeneous magnetic field, and then you hit it with microwaves at the Larmor Precessional frequency. And it's all laid out in the book over here, the paper written by Frederick ALZAFON. I've gone over this a couple of times at APEC. Anti-gravity present technology. This was actually published in 1981, and they replicated the experiment in 1994, apparently, with 80% weight loss within the first second. So I thought it was a pretty promising experiment to try. It does have a very high benchmark to enter this experiment because you need a microwave source, and it needs to be coherent microwave source. So it's kind of hard to just use a regular microwave generator. We're using a traveling wave tube. We also have a klystron that's capable of 3,500 watts. The traveling wave tube is only capable of 20 watts. We're having trouble with the waveguides in order to get all the energy into the test sample. This is pretty much laid out over here. This is the waveguide. I'm sure it doesn't look like this exactly. And you have the north and south pole of the electromagnet or whatever magnet you are using. And what that's supposed to do is create a state of dynamic nuclear orientation where the nucleus of the atom is actually oriented, and that should detach yourself from the Earth's gravitic field and possibly the inertial field. There's a couple different explanations to how this experiment would work, if it is successful. So there's more theories than there are experiments in this regard. We've also worked extensively with Thomas Townsend Brown's work with the gravitator. He calls this the Byfield-Brown effect. Really, it's all about Thomas Townsend Brown. This is actually the only paper where Byfield is mentioned. And so far, our replications have had mixed results. We had one guy in Vietnam, Nam Tran, who tried these experiments. He's always getting positive results, and then he sent over his capacitors to us to try them, and we were getting null results using our DC power supply. And we've since realized that the power supply may be, the signal input to the parallel plate capacitor may be more important than the capacitor itself. And given the type of technology that he had at the time, it's possible that it wasn't a very clean DC signal. There might have been a DC bias with more of an AC form on top of that, or an inverted sawtooth. And that is something that we're looking into. We actually have the components to build that and try that experiment in that fashion. I don't believe this is warp drive right now. Our current theory is that it's more of a electron rocket of some sorts, and it would create a bit of propulsion, which, when used in conjunction with the dynamic nuclear orientation experiment, which will pretty much remove all the inertial mass of the craft, you can then use a small amount of thrust to propel the craft in whatever direction it is you want to go. And that's That's kind of what like Mark McCandless's ARV picture shows, where you have the parallel plate capacitors in the base, and there's these big coils, and there's an aluminum flywheel. It's kind of important to use aluminum for this because aluminum maintains its dynamic nuclear orientation better than most materials. The way the dynamic nuclear orientation is created is by applying the homogeneous magnetic field, which, as Todd mentioned, is pretty difficult to achieve. An EPR electromagnet is, the ideal. That's what's already that's the standard approach. But those things are very big and very expensive and hard to find. We do know of one that's in South America in a dumpster that we might try to salvage, but it's been there for a couple of years, so it's probably all corroded. But these devices are pretty hard to find, so we had to build one ourselves. Then you have the sample in the center of the homogeneous magnetic field, and having a sample in the center of a homogeneous magnetic field, what that does is it orients the electrons based on the strength of the magnetic field, and they precess, which is the spin of the axis, at the Larmor precession, which is way up in the gigahertz range, which is why we have to use microwaves. So it's really about tuning the microwaves to the strength of the magnetic field and pulsing the microwaves as well, because every time you pulse the microwaves, it energizes the electrons, and then that orientation can then, when you turn off the microwave force, can then transfer its orientation to the core, and you slowly build up a orientation in the core, and basically creating nuclear magnetism, which is pretty much what this effect should be called, in my opinion. And once you have that, the craft should lose its inertial mass and detach itself from the gravitic field, because second law of thermodynamics states that everything goes toward a state of entropy, goes from order to disorder. So in the core of an atom, we can expect there to be a lot of entropy. There's all the subatomic particles are probably spinning, precessing in all different directions with very intricate spins. And it's possible that that is what creates the inertial frame in the first place, by having all these spins and these precessions and precessions of precessions. When you move an object through space-time, what you're actually doing is you're adding inertial energy to it, or kinetic energy to it. What you're actually doing is energizing the subatomic particles in the core of the atom, which is where all the mass is stored. And then when it hits, when the baseball hits the bat, all those spins all change. But if you orient all of the spins and they're no longer incoherent, you make a state of coherent matter, the craft will then essentially become weightless. And as David Alzafon stated in his book, he actually wrote a couple books on this. This is the son of the inventor, Frederick Alzafon. So this is David Alzafon's 2 books that he wrote, and they're published on Amazon. That it's also possible that this can create an invisibility system, because we're all interacting over here, like even on this table, we're interacting with the electron field. We're not interacting with the core of the atom. The core of the atom is what creates the inertial mass, but the interactions that we're having here are really with the electron field. So if you oriented all of the electron fields, it's possible that light will be able to travel straight through the hull of the craft, and that can explain many of the phenomena that I've seen around flying saucers and such. But this does not create propulsion. This just gets rid of the inertial mass, if it works. And propulsion can be created with possibly with this experiment. We're also trying the Podklanov impulse experiment using superconductors, and that paper is over here. This is from Podklanov. You're all very familiar with this. This is actually from Tim Ventura's American Anti-Gravity, and they used a Marx generator similar to what we have over here, and we are trying to build a Marx generator ourselves. We have a whole bunch of capacitors, and Jeremiah can show you what we are doing with that so far.
Yeah, so we went on eBay and got a bunch of these surplus 30 kV 1000 picofarad capacitors. They're really nice and decent polypropylene capacitors, so they'll have a very low ESR because of the technology that's used, and they also have a fairly high resilience to partial overvoltages where they can still operate even if there's a problem with one of these gaps. So we got a total of 8 of these or 10 of these boards. Each contains 8 capacitors. We were missing one. We went through and tested all of them. We found a total of 7 bad capacitors that we're not going to be using in this system. So what we ended up with is a bunch of these really nice thick pieces of printed circuit board here with some terminals, and we matched ball terminals and some metric stainless steel screws. So this is all stainless hardware with these points. And what we're going to end up doing, let's see if I can grab the board out of there, is in order to control the discharge voltage, the nice thing that we got in our eBay purchase is that these 2 boards are mirror images of each other. So we can put them on hinges, and by placing the ball electrodes between the already positioned points on these boards and the spacing, which is already 30 kV, same as our capacitors, we can adjust the discharge gap and control our output voltage and our output power. So we're going to be reconfiguring all the capacitors that came on here, and I think we've decided on a 960 kilovolt system that gives us 2 capacitors per set. So it's just banks of 2 caps all in series all the way up. And this is what we're considering for the pocket off impulse discharge. So our 2 options were, we hear you, Jeremy, what's up? Okay. Can you hear me now? Okay, it's the lapel mic then.
Why don't you just grab mine?
Why don't you just shut yours off and I'll turn mine on because it's already attached to me.
Oh, okay, it's been turned off. Okay. Sorry about that. Technical difficulties.
Can you hear me? Or am I still coming through quiet?
I can hear you.
Okay, cool. Then that's good enough. Yeah, so our two options for our Marx generator are we can use 64 of our capacitors. That gives us a total of 28.8 joules of discharge energy, 960 kV impulse. Now, the advantage of a higher voltage in the Pakhanov impulse discharge experiment is that any distance between the superconducting emitter and the target electrode, we can get a slightly farther distance. We can get a larger quantity of electrons in that plasma stream because of that greater distance. And also we have a higher electric potential that's immediately presented from the Marx onto the surface of the superconducting emitter. So we are thinking about going with a higher voltage just so that we have some wiggle room in order to guarantee we get a nice even surface plasma discharge, because we want that initial high voltage impulse. And we don't want it to get stuck in just one plasma stream. We want that current to expand wide enough with enough potential behind it where we have a quantity of electrons available to cover the full surface of the superconductor and guarantee we get current flow through any flux pinned regions that are already present. The other option was that we could use 72 capacitors and get a slightly higher discharge current and a total energy of 32.4 joules. And that would limit our output voltage to 720 kV. It would make the Marx generator slightly smaller, and because it's physically smaller, the distance that electrons have to travel through the whole circuit would be consequently shorter, which would give us technically a slightly faster impulse. So even though we only have a small difference between 28.8 and 32.4 joules of discharge energy, we should have, with this configuration, because it's physically smaller by 1/4 of the total length, we should have a consequently faster wavefront. So we're still negotiating that. We think we're going to go with the higher voltage, but we would certainly appreciate input from any of you as far as what's going to happen in the vacuum chamber and whether or not we need better current or higher voltages in order to achieve that even surface discharge plasma that Pakhanov talks about as a necessity for making the gravity impulse work. The other thing we have, just to kind of go over it, we have some YBCO superconductor. According to Poor and Pakhanov, they were custom-made superconductors that both scientists used, and so we're using commercial superconductors. We're not sure if they're actually going to be suitable for a proper replication of Pakhanov, but we're going to go ahead and go through the motions and do everything as if we had the right superconducting material so that we can get set up for it. That way, the only thing that we have to do is mount our superconducting emitter if we need one custom centered. Electrically bonding the superconductor to the surface, we found out about the bilayer effect thanks to Poer, and how you have these Josephson junctions inside that superconducting material by injecting certain insulators dielectrics or other materials into the mixture. And so we have to figure out how to properly electrically bond our superconductor to our Josephson junction material, whatever we choose to use. And in this case, we're going to use indium. We think we tried with gallium live on air the other day, and it was a terrible disaster. The gallium did actually stick when we applied some pressure with some electrical tape on the outside, just to sort of pull the two pieces together. But ultimately, gallium is its rate of thermal contraction versus the copper that we use to bind and the superconductor. They're all far too different from each other, and it peeled away.
So, that happened right at supercritical levels, like literally
it happened
right
about
there.
10 degrees just before we hit supercritical. So it held up pretty well for most of the part, but once we got down to the real low temperatures, something broke it off. So we're going to try indium instead. Indium is apparently a much more common used material. It also doesn't tend to eat into metals, which is why it's used in laser diodes with gold surfaces, so it doesn't eat through the gold and cause an electrical contact issue. Then we have to work on a vacuum discharge chamber. In this case, we're just using an acrylic tube. We're going to use a 1/2 inch thick wall, 4-inch diameter, cast acrylic piece, probably about 2 feet long, so that we can see the inside of the chamber and watch our plasma discharge. We think this is really important because, according to Potkonoff's papers, the shape of the surface of the plasma discharge coming off the superconducting emitter determines the consequent intensity of the gravity impulse. And so he was reporting that what happened is a almost cylindrical like form came off as a plasma from the surface of the superconducting emitter. And if we don't actually see that in our application, then we know we have not faithfully replicated based on the reported information in his paper. So that's something else that we're going to do. We think we figured out the bilayer alternative thanks to POR. So we're going to work on that too. This is where we're at with Eugene Potkonoff stuff. And then the other thing that we're really excited about this month is replicating Richard Van Durek's complex electric field systems, because he's got 2 great alternatives that he talks about. Last APEC meeting, he blew my mind, and probably many other minds, because he presented the mathematics and the necessary systems to talk about what happens to electric charges in different frames of reference, and how you can derive a non-zero force from a solid body where you have electric charges flowing in different frames of reference or electric currents flowing in different frames of reference. So we're going to go ahead and replicate one of Van Durek's older systems. He has a rotary disk system that uses 2 physical disks. One moves, one doesn't. One is called the dot product disk, and the dot product disk here is made of very small particles, usually microspheres, of some conductive material suspended in epoxy or situated in such a way that when these tiny little microspheres are charged up and you feed them with an electric potential, that when there's a very small change due to a relativistic field being applied to them, the change in their potential does not have the ability to jump over and conduct current. So basically the charge stays on these microspheres, it doesn't leave them. And as a result, they're able to experience a non-zero force. So our dot product disk, we have some new epoxy. Where is our epoxy?
Right there in the epoxy box.
Great. I'm going to pull that down.
Got the
Especially because Richard is, in the audience today.
Just pull the whole box down.
I think I'm going to open this up and pull out the data sheet here. Epoxy cast 670. So this is an incredibly thin.
No, that's not the
stuff here.
690.
Oh, the 690. That's the new stuff we're going to work with. So the 690 made by Smooth On, we're going to try to use this as an epoxy. It's incredibly thin. Trying to see where our centipoise rating is on our sheet. Either way, basically it's mixed viscosity here. Yeah, here we go. 280 centipoise. So it's a very, very thin epoxy, and I think that's going to really help us reach that saturation for our microspheres. We have 3 materials that we can use right now. We have a bismuth powder that's mostly spherical. We have a aluminum powder that should be satisfactory. We have a nickel silver powder. And which is that I pulled out? The magnesium powder that I tested when I just did a pour test to sort of see if you've ever done a fine grinding on a powder and you try to pour out a large volume of it inside of a container, just tilt the container back and forth. If it's spherical, you'll notice that it just seems to flow almost like a liquid. It doesn't act like a powder or a solid, it doesn't bunch up. And so we have some magnesium powder that exhibits that property, and we're going to go with it's mostly spherical and try to inject a very large quantity of that to electrical saturation inside of the epoxy mixture so that we can charge up the microspheres, but then allow them to maintain their charge as we rotate the cross product disc. And so we'll get to that.
Well, what about the bismuth powder?
The bismuth powder is another possibility, and the great thing is we have multiple samples and plenty of epoxy, so we can make many different dot product discs that are going to allow us to try these different materials and their various properties.
We also have copper powder as well.
Indeed, we do. The copper powder is pretty rough. It seems like it's starting to oxidize if you take a look inside. So I think we might avoid that, or we'll have to do something to it to treat it. So the cross product disc, we just need a very smooth conductive surface so that electrons can freely flow around it. The thinner that surface is, the better it's gonna react. We want to keep them constrained down to that one axis as the cross product disc is rotating. Now, last time Richard revealed a very important piece of information, which is you actually get better results if you rotate the dot product disc. Now that I haven't mathematically comprehended as to why you may get better results if you rotate the cross or the dot product disc, but my thinking was that the dot product disc is going to also experience forces from electrostatic charges on the body of the enclosure that it wouldn't experience at all if it was stationary compared to the body of the enclosure. So perhaps that's one explanation. The cross product disc is just going to be a CD-ROM that we stuck a voltage multiplier on and blasted off all the metallic coating of it. So we had a nice piece of plastic to work with, and then we laminated that CD-ROM with a piece of thin film mylar using some adhesive, and pressed it down with some pressure to get a nice even surface. So we'll be spinning that up to 25,000 RPMs, and we have just another CD-ROM which all the printing was removed from, so we have that metallic coating, which is just a few ohms across the entire surface. That's another good solution for a cross product disc where electrons can travel around it, and you don't get the equal and opposite charges because the electrons are free to move across the surface of the disc.
We also have those really cool hobby electric motors that are capable of like 1 horsepower. Those things are tiny.
Yeah, those are going to give us quite a bit of torque, especially if, according to Richard's paper, what happens is as you generate a linear motion from this system, you end up with a resultant torque on the motor that causes it to slow down, or it loads the motor. So those nice strong motors at high RPM will be able to provide plenty of torque. Not to say that we'll probably ever even come close to loading a motor, because the speeds that we're talking about in the voltage differentials between the dot product and the cross product disc are not realistically strong enough to cause us any significant power draw. It'd be wonderful if we could get materials that would allow us to do something like that, or we could take a 1 horsepower motor and convert it straight to linear momentum and use all that energy, but I think we're a long ways away from that yet. Now, right now we just want to test it out, make sure that we understand properly what was presented, what Richard's theory implies, and how to actually implement it. And then we want to try our best to try to do a proper Eugene Pakhanov discharge, making sure that our experiment and the observations we make match the observations in the paper. And thanks to the papers that Tim sent over, we have lots of information from POR, which is effectively on the same thing, which we now can use to derive what's going on with Pakhanov.
Right. Talk a little bit about the rectifier tubes. We have a couple of different options on those.
That is a good point.
Some of them are still on their way. They're coming from Russia, I think, the 400 kV ones. We have a couple tubes up there. What kind of tubes do you think we need for this?
So what we ended up ordering is we took a look on eBay and tried to find some reasonably high voltage tubes, because when Ben Dirk produced his patent, in his patent he talks about using several kilovolts, and we wanted to try to really push the boundaries of what the dielectrics could take. So we're going to try to go into the double-digit kilovolts, and in order to do that, we needed some double-digit rectifiers that could handle that voltage. So we ordered some from Russia. They're coming in, and those are going to allow us to isolate our electrical power supply or our power source from the physical device itself, so that electrons can't backflow. And if there's an imbalance due to the changes in the electric fields from the complex electric field interaction, that we're not going to have electrons flowing into or out of ground or the power supply to try to neutralize out those changes in potential. So we're going to use rectifier tubes. We're going to power them off 18650 batteries or other small LiPo batteries, so that we can completely isolate that system and properly test what Ben Dirk has presented.
Right. Also, the oscilloscopes and any test equipment that we plan on attaching to this experiment is also going to be floated using a UPS system, completely separated from ground. So I know that's very important.
It was that big eureka to realize that most of the reasons why we were having problems and erratic results had everything to do with the fact that we always had some kind of leakage or connection to an earth ground. And that caused us major issues because an earth ground, effectively an electrical connection between 2 points in any system ties those two systems together into the same frame of reference. And it's wild to think that you can connect different frames of reference with a piece of wire, but that's effectively what you're doing. So you have to keep them isolated, and to finally have learned about that and realized why we've seen some effects anomalously in very fast systems where the resistance of our electrical connections was actually not sufficient to totally separate out the frames of reference. That's why we've seen the effects. It was a big eureka to realize why. And again, huge thank you to Richard for presenting that so we finally understand.
Okay.
Okay. Yeah.
Also,
yeah, I've been listening here, and I probably had a couple comments on what you had to say on this.
Yeah, please.
You had a question on rotating the dot product disk.
Yeah.
Yeah. So what you want to do is, one of the things the dot product is generating is a scalar potential. So when you rotate it, you're effectively taking the charge and accelerating it 90 degrees to its relative motion. Well, that causes the scalar potential to basically decouple from the potential. So it'll build up around the individual particles as, say, you rotate them. So that's the reason why you really want to rotate the dot product disk too, because you're going to end up starting to build up the scalar potential. And then that actually, the experiments we've done recently seems to show that that has a much greater effect than the cross product disk. So if you can, that would be a desirable thing, is to get your dot product disk all balanced out. And if you can rotate that in the opposite direction as the cross product disk, I think you'll have a better effect. But yeah, it sounds like you're doing everything correctly. Just make sure you don't get any past the ground. And I think you should start seeing some good results. And of course, you'll let me know when you start putting it together, right?
Absolutely, Richard. I mean, you're the reason why we're doing this particular experiment, and what you presented was, as we said, a huge eureka. It just is it's a total difference in understanding why some things happen the way they do, because we've seen strange effects for a long time. I've been doing this for now going on almost 22 years, and I've seen a lot of really weird things happen, especially around very high currents with capacitor discharges, around very high impulse voltages. And I've noticed a trend with these various things that I've seen, with objects moving on their own or electronics being triggered by an EM pulse that should have never existed from the amount of power that we had, but it seemed to go a really long distance. It finally makes a lot of sense as to why you could be generating scalar potentials and how they can transfer. Because the great thing about a scalar potential, right, is that you can't really block it. It's a point, or it's a charge that's going to expand out, and that charge field is going to have an effect on all other objects. You can't really block a change in local electric potential from one potential to another. It's going to penetrate, and that gives us the unique ability to change the field geometries of that generated signal source and screw around with scalar potentials in a way that I don't think we've ever even realized we should be looking into.
Yeah, and that seems to be the key here. Is those scalar potentials, once you're able to generate them, they'll persist there for a while too.
Yeah, Jeremy, go ahead if you have live chat questions.
I can't hear you.
Jeremy, go ahead if you have live chat questions.
Your sound just went completely dead. I can't hear anything.
No, it says it's on.
Yeah, I can still
I'll
hear
just
you
stay
guys
close to
fine.
Mark's mic, I guess.
That's better. I just came back.
So live chat questions, Jeremy?
Over here we have our power supply racks. Just want to show you this real quick. This is for the Alzaphon experiment. This is a 30 volt 40 amp or a 40 volt 30 amp power supply. It's one of the really old kinds, super heavy, had to ship freight. That's to supply the super stable laminar magnetic field for the electromagnet. Up on top over here, we have a Maxwell 45 kV. This came out of Sandia Labs, used equipment. It's 45 kV, 8,000 watts, and I managed to get the matching capacitors, also 45 kV capacitors here locally. So that is for the lower voltage version of the impulse experiment with PodClown with superconductors. In order to read everything, we got this out of Singapore. It is 16 gigacycles per second scope. The only way we could afford a scope this fast is by getting a super old one that still works. And as you can see over here, we actually had to buy these. I don't know if you guys can still remember these things. These are coming out of museums, floppy disks and a floppy drive in order to read the data. But the scope still works, and it probably costs as much as a small house when it first came out. Over here we have, this rack is really the super high voltage rack. There's a scope attached to it as well, which we had to shield from our last experiment. This was for testing the capacitors. But basically this rack has a gamma 125 kV 5 milliamp power supply, and below that is a 10,000 to 1 voltage divider, and that's hooked up to that oscilloscope. So we're able to see high voltage potentials on a standard oscilloscope. We could also hook that up to our 16 gigacycle per second oscilloscope to measure the impulse velocity rates, for any of these high voltage, high current experiments. And that's most of our equipment right now. We have also in this corner, this is something that Jeremy brought in. This is a 5 kV half amp power supply that's going to be used for the Klystron. Jeremy actually found that on Craigslist from a lab that was going out of business, and this is something that we couldn't find anywhere else. So it was amazing that he was able to bring that down to the lab for us, and we're currently working on that. I think that we're going to have to bypass one of the safety relays in order to just
we're going to bypass.
I just want to comment on how heavy that thing is. That
Yes.
I had to...
Oh yes.
How did you get that into the car on your own?
That thing is very heavy.
I think I had help. I had to get help. I could not have moved it by myself. No, I did have to have a second person help me move it and transport it.
It's got a huge plate transformer in the bottom. That's a beast.
You can see the front dials. Look at the size of that dial. That's my hand.
Yeah, that's some like 1940s old school equipment. That thing's diesel. That thing's built. You don't find equipment like that anymore.
Yeah, so I think this is the interlock. There's the problem with the that transformer is blown out. It's a 12-volt transformer, so the interlocks are not working. So we could either replace the transformer, or we could just override the interlock. It's something that we're considering.
At its core, all that thing really is effectively is a voltage divider for some meters in current, a variac, and a huge plate transformer that has multiple wiring configurations. And all we have to do is give that variac power to feed the plate transformer. The rectifiers are already in place, and everything else should pretty much work straightforward. There is no reason why we need an interlock in that system if we're going to install it in a cabinet and bring out external cables anyways. We're going to be setting it up in our lab, and we have sufficient signage to indicate the dangers of the system.
And something else that was really cool that he got from that same lab, they couldn't explain it to Jeremy why they had it, was a whole bunch of waveguides that were tuned to a very specific frequency of 6.21819 gigahertz. And there's a ton of tuning that went into all these waveguides. There are several pieces of waveguide all tuned to a specific frequency, and that will work wonders for our experiment, because if we can lock the frequency in at a certain point, we can just use this power supply over here to change the flux in the magnetic field, and use that as our variable to finally find the Larmor Precession frequency by changing the magnetic field strength.
Well, that's pretty much the summary of what we already have going on. We are planning on a few other projects that we haven't really written up yet. These are the focus points right now. We don't want to get our hands in too many baskets. We want to focus on the projects at hand, which is Paklanov and Richard Van Durek. So if we can get far enough along on either of those that we can make progress, then we'll move on to a few other projects, perhaps this month or the following months. But that's the update from the Falcon Space Lab. That's where we're at right now. We're testing everything that we can, and we're focusing on the things that we think that we have at our current skill level and our reception with the community, things we can actually do and test properly. Because we're not just trying to put together things that look kind of sort of similar to what the scientists did. We want to replicate as accurately, as faithfully as possible.
Exactly. That's the most important point, is to be able to actually replicate them in the lab. And I'm also excited about the Alzfon thing. I've been working on it for a while, but we need to figure out the waveguides. Until we figure out the waveguides, it's all just a waste, you know.
Yeah, the real trouble we're having with waveguide issues right now is that we can beam out that signal at whatever frequency we choose from our frequency sources, but that signal is basically hitting the sample and then flying past it and being lost in attenuation to the outside environment. So what we need is a resonant chamber that we can tune for the frequency ranges that we're using, which is the 8.8 to 9.5 gigahertz range. And then we need to design something else, perhaps more powerful, for our klystrons range. So that way we can get a nice Q factor. We can get many, many times more power into the sample so that the sample itself absorbs that microwave energy instead of it just being lost in the environment or causing us SWR issues down the line.
And just reading SWR on a microwave waveguide, I mean, there is no microwave waveguide SWR meters out there. It's literally something you have to build yourself. And we're talking to all the professionals in the field. It seems like it's a real specialty. There's very few people who understand this stuff to the level.
Sort of an industry secret, hey?
It's an industry secret, yeah.
Like, how do you design a proper waveguide with an incredibly high Q to get energy into a sample?
How do you measure the Q in the first place? And how do you measure the reflected energy? These are all issues that we're going to have to work on.
Not stuff that you can easily Google, because I've spent many hours on there trying to find this stuff out. But unfortunately, it seems like it's just it's a bit difficult. Maybe it's because we're just ignorant of the right terms to use. We may not be looking up at the right information, or
we don't even know the question to ask.
Right, exactly. We don't know what we don't know. So this is definitely where we're asking for help to try to figure this problem out, so we can test Alzfon properly and get energy into the sample to see if we get good dynamic nuclear orientation and we get good coupling from our microwave energy into our sample.
In terms of capabilities, we also have a 3D printer over here that we can print in resin that we can then cast in any different metal. We have furnaces and we have casting materials. So if you want to cast something in silver, nickel, or bismuth, we purchased a whole bunch of bismuth. It has a high spin ratio. It's a pretty interesting metal. We thought it might be interesting to try something with bismuth. Now, also you have the bilayer setup that was found as a supposed relic of a flying saucer. And if there is something to bismuth mixing with other metals in a bilayer that we can put into the Alzfon experiment, that's something I really want to try. So any help from the community, anyone who knows anything about these experiments or knows somebody who knows how to work with microwave waveguides and tune them properly, that would be very beneficial to what we're doing over here. And like I said before, we do have some limited funding from an anonymous donor, and so far they've given us around $30,000, and this is what we've been able to put together with that. But we have more equipment coming in the mail. We also have a guest house available, and he's offered, like, if there's any scientists who have relevant information to the experiments that we're doing, he's glad to fund them to fly down here, all expenses paid, and we can work on these experiments in this anti-gravity lab right here live. And all of these videos, all of these experiments, by the way, are going to be published live on YouTube. Jeremy Reese and Travis have worked out a system with multiple cameras. You can see our first demo of that, where we kind of made a makeshift experiment just to try it all out. And that was really amazing how we were able to get all the cameras together and run an experiment live on YouTube.
Okay.
What happened?
All right, I just want to remind everyone to smash that like button who's watching this live, and share this video with anyone you think who might be interested. Again, we're going to be making like short clips of highlights and of key points and things. And again, we invite anyone from the audience who has information they'd like to present and join this community, anything that could contribute to the body of knowledge, or the lists of or the experiments in the lab. Anyone who has equipment or anything else like that, or time or lab time that they can offer to run certain experiments, or if they have they can help us run these experiments. Basically, like, the goal is to bring more and more scientists on who know stuff about this, share the information in an open atmosphere, and kind of accelerate the process of R&D and disclosure, really, of the information. Because people think there's a lot of people talking about disclosure right now, but I don't think they're really willing to learn the real information. And put the time in to really wrap their head around this kind of knowledge that's going to take to build the first craft that gets us off this planet. That's really the goal here. I know it seems like quite a achievement for some of the people out there, maybe thinking like this might be 5, 10 years, 20 years. This might take our lifetime. These guys have been working on it for quite a long time already. And that's awesome that they're here to share all of their knowledge and experience with us. There's no better teacher than failure, I say. And the more that we can demonstrate all these other experiments of the past in a lab setting with a group of people that are really real skeptics, that people have a track record that people can trust. If we can vet these out in our own lab publicly, one at a time, it will save so many people so many wasted time, or years of wasted time, and their own wasted research and funds and everything, because there's so many videos on the internet showing these kinds of things. And if we can show them and really vet them out and say, like, this doesn't work, this doesn't work, this doesn't work, that's going to help save a ton of people's time. And if anyone out there has already done these experiments and knows, how to set them up, or has them already, set up somewhere, they can go and show us, okay, we've tried this didn't work, this didn't work. That's really where we need to go through, because, is prove to people that, no, they're in the same time, it's going to vet out the whole, people like Stephen Greer, who claim that there's a secret space program that figured this all out back in the 50s, and if that was the case, I don't know what the heck you guys were doing working for DARPA on all this stuff for the past 50 years if they already figured it out in 54, like Stephen Greer wants to tell everybody. Again, if they did, we're going to figure it out and we're going to find it. But if not, and this really is the cutting edge in humanity's evolution to the stars, then we're gonna hopefully put the laboratory and the team and the scientists together to bring disclosure on that level, and hopefully the scientific community is open to that, and and open to contributing with us, not just, the there's naysayers that just want to fight everything and say, oh, you're not going through the conventional channels and stuff, like this guy was saying in the live chat. You should be doing peer review. Peer review will come, like, when we get something that actually works and is worth, writing a paper on. I want to definitely write papers with you guys, and we have a team of people ready to do that when our lab does have success. I want to write papers and publish it in the peer review and get it out there, but we also have a kind of a fear and a skepticism of that whole process, that that whole system has been used to suppress information like this in the past. So we want to do it publicly first, demonstrate it, and show people how to do it, and whatever works, show people all the stuff that doesn't work, and then when we get it, we know how it works. We want to have led up to it, and people who have followed it to really have the knowledge and the background to understand the science behind it when we do have that success in the future. And I really have confidence that we will, with this team and the amount of people that are coming out of the community and bringing us support and hope.
Can you guys hear me all right?
Wonderful. Yes.
You're a little quiet.
Wayne has his hand up also. I should mention that.
Yeah, Wayne, go ahead.
Yeah. Hey. I just wanted to do to share a couple little things that I've been working on and will be working on in the near future. and it relates a lot to what Todd was sharing about the NMR and what you guys are working on and have worked on with Elzaphon and all that. So I've been thinking about how to maybe work this thing at lower frequencies. So just using these, I made this last night. So this is going to be, there's going to be two Helmholtz coils oriented perpendicular to each other. So the one will produce kind of a weak magnetic field. I'm aiming for about 30 Gauss. And then I'm going to have across from that perpendicular, I'm going to have RF. Well, it won't be RF, something around the 20 kilohertz. So I'm aiming for around the audio frequency range. And I'm going to put some, I kind of calculated it to work with bismuth because I have some powdered bismuth I'm working with. And so I just put the sample in there and maybe suspend it. So that's something interesting. And then here I had inside here between these two neomagnets is an epoxy casting with bismuth powder in it. And so I was and will be playing with that, putting some AC magnetic fields in here and just putting it on a scale and seeing what happens with that. Here's an older Helmholtz coil I made. And yeah, so this here is a capacitor I made. It's got bismuth powder in the middle with epoxy and dielectric. And I was going to test it with different, like high frequency, high voltage currents. I'm thinking that might excite some effects inside the bismuth atoms. So yeah, I just wanted to give a little quick update. I'll be posting all my stuff on my YouTube channel, Fail Forward Research. And yeah, that's about it. Thanks.
Yeah, let me compliment you on the quality of your builds now. I mean, they're looking really, really good. You're spending a lot of time putting them together as compared to the earlier experiments where we sort of crashed course our way to figuring this stuff out. It looks like you're trying to up your game, and that's awesome to see.
Yeah, I don't have a lot to work with, but you know, I'm trying to do the best I can. So yeah, there's a long way to go. There's a long way to go. Yeah, but
great job, Wayne.
Yeah, thanks guys, and look forward to all of what you're working on there. That's going to be amazing.
The other thing that I wanted to point out for sure, especially amongst this community, is once we build this equipment, you know, we may not be the biggest experts in the industry on exactly how to use it, but we have the equipment. So when we have a 1 megavolt Marx generator, or a 960 kV Marx generator, and you have an experiment that you want tested on it, or an apparatus that you want hooked up to it, I mean, that's something we'd be interested in testing out. So we just want to sort of extend that offer out there to people in this community, where if you have devices that require weird equipment or specialized equipment like the types that we're setting up here, we would be interested in collaborating with you and using what we've already acquired to try and test out your ideas and theories. And we can follow them like a scientific procedure and do exactly what you recommend to do to make sure that we test what you're looking for.
Wonderful. Well, gentlemen, do you think we should call it a day today?
Only one way to find out if he'll answer, and I'd say give him a call.
Well, no, I mean, yeah. I think it's probably time for us to wrap things up for today. So
yeah, I agree, and I'm just typing some stuff away and getting some links together. We're going to put some links together for this whole talk. This was an excellent discussion. I learned a lot from our guests. Thank you, Gary, for being part of this, and thank you, Todd, and thank you as always, Tim, for putting this together. And
some applause for Tim.
Yeah. Well, Gary, thank you again very, very much. And Todd, you as well. You're hiding on my screen, but I think you're still here. Yeah, there you are. I'm losing. There you go.
And
Okay.
thanks to everyone who contributed. Anyone wants to give a shout out real quick to the end for a link or anything that they want to give a shout out, they can go ahead and do that. And then we'll go ahead and wrap this up for the day. Fail Forward Research, that's Wayne. I'll give a shout out to him. And then also you guys can check out Join the Technicians, although Jeremiah is not really doing much with that channel anymore. And then I'll post a link to Clay's website for his disclosure project there. He's in the chat as well.
And we'll get Gary's material up as well. So, and then I believe Todd
Gary,
definitely send me over links.
His link already too. Yeah, sorry.
Wonderful. Okay, well, thank you again.
I just want to make a shout out to Tim Ventura, who made this entire thing possible. Let's get it.
Well, thank you, sir. Okay, on that note, let me hit the stop button and we will wrap this one up.